After today's lecture, you should be able to do homework 2. Homework 2 is coming. Today's lecture, what are we going to focus on? So, some recap. Last week's lecture, we talked about a very important concept called driving point. Driving point concept is useful in the sense that it allows you to analyze circuit in a very simple manner. Okay? We go through many examples. I hope you are impressed by how easy it is. I can just look at the circuit and write down the equation. Okay? That should be the right approach for circuit designer. Of course, it doesn't work all the time, but I guarantee 90% of the time it will work. Now, there are some circuits that is totally new, and you don't know how to approach them. If that is the case, you always have the fundamental. Fundamental means that you replace all the transistor with hybrid pi model and derive everything. It's tedious, no doubt, but you only need to do it 10% of the time, so that is okay. Okay? And then we further go through single-stage amplifier, showing you how we can do that. More importantly, we show you what are the important single-stage amplifier. I hope you still remember. For BJT, we have common emitter, common base, and common collector. For MOSFET, we have common source, common gate, and common drain. And then we move on to talk about two-stage. Two-stage, the important thing is about how I combine two different single-stage together to accomplish something, okay, to accomplish something, or to obtain some desirable characteristic. Okay, so two-stage, we covered different kind of combination. I believe some of a very interesting one coming up. I hope you still recall, cascode. Agree? Very useful thing to boost out the impedance. And later we introduce folded cascode, a variation of cascode. And also Darlington pair, right? This is a very special kind of combination that gives rise to interesting structure. Okay? Now, today, we are going to base on what we have learned so far. Now, so far, all the analysis that we have done is the so-called open loop analysis, meaning that there is no feedback involved, right? Just from input to output, only one path. It doesn't go backward, okay? And this kind of amplifier might sound very easy to you. You're probably wondering why we do with this kind of amplifier. But if you look at all the RFIC design nowadays, we're still doing this kind of single-stage amplifier design. Why? Because if you think about RF amplifier, you want high frequency. If you want high frequency, you don't deal with too many transistors. The more transistor it is, the more parasitic it is, right? So it's like accompany too many people is not a good thing. Okay, a lot of politics, that's not good. So same thing. If you want RF amplifier, keep it simple, so that you can go high frequency. Another thing is also about noise, right? RF amplifier, you want to keep it simple, so less noise that you can hear, because every transistor contributes noise. And then we'll move on to talk about differential pair. This is a very important or critical element, or I wouldn't say element, building block. This is fundamental building block for op-amp. So differential pair, we are going to analyze or scrutinize it in very detail, focus on what are the important things, what make it interesting. And more importantly, I'm going to highlight, a lot of people think that as long as you have two paths or dual path, that is considered differential. So there is actually so-called differential circuit, which we like. And there is another thing called difference circuit. Okay, difference circuit is kind of no choice, it's better than none, but it's not going to be as good as differential. So I'm going to highlight that. And then, of course, the interesting thing is about current source. If you think carefully, we always like using current source because from our probably first lecture, if you think carefully, all the small signal parameters depend on current source. GM for BJT is IC over VT, current, right? Now, for MOSFET is square root 2kn ID, drain current. So almost everything, all the small signal parameter, I can give another example. R0 for BJT is early voltage VA divided by IC. For MOSFET is 1 over lambda ID. So all the small signal parameter is depending on current. So if you use a current source to bias a circuit, your job is almost half done because you know the current, you know everything. Instead of using voltage, if you use the voltage, you still have to go one step, try to solve what is the corresponding current. So current source is a very popular way of biasing the circuit because it makes the circuit very controllable. Once you determine the current, everything is fixed. Okay, so we are going to look at different way of implementing current source. And then with the current source, it actually bring a very important concept, active load. Active load means that you are burning some power to create a load. Frankly speaking, to create a load, you don't need to use additional power. A resistor itself is the so-called passive load. Right? You already consume power. You don't have to give additional power for him to behave like a resistor or behave like a load. Okay? By itself, it obeys Ohm's law. But there are some undesirable characteristics for resistive load, passive resistive load. So we're going to look at how by burning a little bit more of power, I can actually make some desirable characteristics. So let's go through this classified under RF amplifier. It's more popularly known as optical amplifier. Can you just show me your test result?
Yeah. Don't know where it's like this.
Okay, I can see. Yeah, this one. So take my word for it. 1 bar, not 2 bar. Okay? Now, trans-resistant amplifier, I believe I mentioned this during last lecture, is a very popular way of for optical communication. Okay, so here I also show the example. You can see that we use photodiode. So this photodiode will generate current depending on the light shine on it. Why this is very popular? If you remember when we talk about Mueller effect, any feedback register, you can actually reflect over here and becomes R1 plus A. Remember? That is Mueller effect, right? Now, the problem with photodiode is that they always have parasitic capacitor, right? Any diode is reverse bias, it will have capacitance. So if you think carefully, this actually form a pole, low frequency pole, RC. This RC determines how high the frequency can go. And that makes trans-resistance amplifier interesting because if you look at it, due to the feedback register, when you reflect it to the input, it actually gives you a very small equivalent resistance, reduced to 1 plus A times over here. So what is the equivalent pole? The equivalent pole becomes C multiplied by 1 plus A. Okay? So you almost extend the bandwidth by 1 plus A times. Okay? So that is the beauty of trans-resistant amplifier and why it is so popular for optical communication. Okay? So let's see how we can create this kind of trans-resistant amplifier easily. So we use an example of BJT, so shown over here. You already know, if you ignore the register here, this by itself, we cover this. This is common emitter amplifier, right? Common emitter amplifier, and with the gain of minus GNRL. Or if you want it to be more exact, parallel R0, but usually R0 is big. So we already know that. So this is actually having a gain of minus A, which is exactly this guy. And the register that we add in is between the output and input. So this is actually a feedback register. Okay? So let's see. To derive it, let's try to derive the input resistance. So to derive the input resistance, we need to figure out what is V in over I in. So that will give you the characteristic input resistance over here. So for BJT, we note that the I in, the current source, according to KCL, consists of I2 and I1. So I in equals to I2 plus I1. Now I1 is easy. I1, you look into the base, what you see is the equivalent resistance for this transistor, which is Ri. So to derive the I1 is basically using the Vin divided by Ri. That is how you get it. And then what is the Vout? The Vout can be obtained assuming this is Vin, and then plus the potential drop across the resistor R, and you end up having Vout. So therefore, Vout is given by Vin. Okay, the potential drop, so I have to subtract away the I2 multiplied by R. But there is one way of obtaining the Vout. There is another way to obtaining the Vout. It's basically, what is the total current going through RL? So the total current going through RL is basically beta I1 subtract away I2. Beta I1 subtract away I2. So if you do that, you are going to get what is the total current flowing through the RL, and then you multiply by RL. You're probably wondering why there is a negative sign. Remember, we are doing AC analysis. So when you're doing AC analysis, all this DC voltage is actually considered as AC ground. And the current is flowing downward. Okay? So the top is higher potential, because flowing downward is high potential to low potential. So the top potential is higher potential, which is 0. So the lower potential therefore has to be negative. That's why you have the negative sign over here. So after some algebra manipulation, so you go through this manipulation, you obtain Vin over I2 is given by this guy. Okay? That is not the full story, because remember, what is your Rin? Rin is equals to Vin over In. So if you consider this guy as I2, this guy as I1, so it is like if I have two resistors, okay, this is In, this is I2, this is I1. I1 you already know, this is Ri. Now with I2, that is what you obtain. Okay, this is Vin over I2. So you figure out this resistor, which is this guy. So to figure out the total Rin is quite easy, right? It's just two resistors in parallel. Okay, so therefore, once you know this resistor, to get the Rin is very easy. You just need to do this guy parallel with Ri. So we go through all this trouble to show to you one very important characteristic. We successfully reduce the effective input resistance. That is the beauty of this trans-resistance amplifier. We reduce this effective input resistance by the gain, 1 plus GMRL. Okay, and what is the advantage of that? When you combine with the capacitance, parasitic capacitance of the photodiode, you are able to get wider bandwidth, because the RC pole gets smaller. Okay? Now MOSFET is simpler, so if you try to replace this guy with MOSFET, you don't even care about I1, because I1 is not there. Okay, so all you need to do is simply I2. So In becomes I2. And you go through the same thing, your Vout can be obtained, first looking at Vin, and then go through the I2R drop. Or you can directly see what is the total current going through RL, which is the current due to this transistor, given by GNVin, minus away this I2, okay, multiplied by the RL, the negative sign mainly because the top is AC ground. Okay, and after some manipulation, you got the same thing. But here, unlike BJT, you don't have to parallel with anything, because the gate resistance for MOSFET is infinite. Okay? Now, so let's look at the Rin. For BJT, we already obtained this guy. So you can see that for BJT, the smaller you can go is basically 1 over GM. That basically assume this is the smallest one. Okay, and you assume R is so small. And GMR is bigger than 1, so RL cancel, you get 1 over GM. This is the smaller resistance that you can get. And then the highest resistance that you can get, you can keep increasing R, making it larger and larger, but eventually, if it exceeds Ri, then it's going to be dominated by Ri. So that's why the input resistance for this BJT-based trans resistance exhibit this kind of saturation characteristic. Initially, it's 1 over GM, it keeps increasing. eventually it's going to flatten out as Ri. Now how about MOSFET? MOSFET, no issue. If you use the smallest R, then you end up having 1 over Gm, same thing. But if you keep increasing R, you see that the input resistance just keep increasing. Okay? Of course, you know you cannot increase forever. Eventually, it's going to be limited by the leakage. Okay? But that is going to be very big, and we don't design trans resistance for such high resistance. It defeats the purpose. Okay? How about output resistance? Output resistance for MOSFET is actually quite easy. So we just look at the MOSFET first. If you look at the MOSFET, this is the output resistance. Okay? Now if you look at this guy, so let's draw the wire slightly higher up. You see that the output resistance for MOSFET actually consists of two things in parallel. The top one, which is RL. Agree? Now the bottom one, what do you see? You see a diode connected transistor. We covered that. Diode connected transistor has an equivalent resistance of 1 over Gm. So therefore, output resistance for MOSFET is quite straightforward. Now for the BJT, we can do something similar. So we slightly move the wire up a little bit. So again, you see there are two things in parallel. The top one, RL, which is here. Now the bottom one, you're actually looking at something like this. Okay, you're looking down something like this. We didn't analyze this before, okay, but we are going to borrow some mirroring concept. So we are trying to obtain something like this. Right? This is what we are trying to do. Why is the resistance looking down like this? But one thing I like to tell students is that what is this? What is this? A pen. Right? What is this? Also a pen. So it doesn't matter whether I hold it upright or hold it flip down, it's a pen. So if you look at this guy, it doesn't matter I look from the top and connect the ground at the bottom, or I connect the ground at the top and I look from the bottom. They are the same. Right? So if you cannot accept this concept, just ask yourself, is this guy equivalent to this guy? Let's say this is R. Is this also R? Right? They are the same. They all give you R. It doesn't matter which direction you look. Now if that is the case, now this guy still doesn't look very familiar to you. It's fine. When you have two things shot together and connect to ground, what I can do is I can connect ground separately. They still look the same. Am I right? They're actually identical. But have we analyzed this guy? We did. If you look at the table, you will see that this is asking you what is the driving point resistance looking up into the emitter terminal, where you have collector terminal grounded and then the base terminal connected to some resistor. And we derive the formula, which is this guy. Okay? So driving point concept sometimes is not just straightforward, use it. You have to be able to flexible, try to see that there are actually something equivalent. Okay, so with this driving point concept, you can actually derive the output resistance quite easily. Now then, of course, the most important thing, what is the gain of this trans resistance amplifier? So starting from MOSFET, okay, we want to find V out over I in. So V out is given by the current source, which is GMV in, minus away the I in, okay, and then multiplied by RL. The negative sign is basically because the top is virtual ground. Okay, and then we can replace V in, because V in is simply given by I in multiplied by R in. And we know R in, we derived earlier, right? So therefore, you replace everything, you end up having very complicated formula over here. So I'm not going to test you derivation anymore. So remember, this module, I'm not trying to test you re-derive everything. So all this analysis is nice to know, because along the way you will see different circuit technique or different way people think about how to simplify the analysis. This is useful. Maybe next time you can use the same technique for other things, right? But once we derive it, I'm not going to test you to rederive. That is not the emphasis of this module. So after derive this thing, very complicated, but if you know what you are doing, eventually you can simplify. For example, I know usually we design amplifier to have a gain much bigger than 1, so I can ignore this guy. Okay, now if I compare these two terms, this is RL, multiplied by some huge number, gain. This is just simply RL. So again, I can ignore this guy. So eventually, after everything cancels, I end up having this nice little thing, minus R. So VR over IN eventually just depend on the feedback register R. Now for the BJT, we can do something similar, but a bit more complicated. So first, we determine I1. Now here it looks very complicated, but here we are using this concept. Suppose I have IN. Suppose this is I1. Suppose this is I2. Suppose this is R1. Suppose this is R2. Now if you have learned your circuit theory 101, you know how to obtain the current. I1 is simply equals to IN, okay, IN, multiplied by total resistor R1 plus R2. The numerator part, if you want to see I1, you write down the resistor of the opposite branch, right? So you write down R2 over here. Same thing, if you want to obtain I2, it will be IN multiplied by R1 plus R2, but you take R1 instead. So that is the parallel branch current. So if you think carefully, you have IN over here. If you want to see the current going through I2, you just have to figure out what is the resistor in this I1 branch, which is Ri. But if you want to figure out the current going through I2, sorry, I'm wrong. No, if you want to figure out the current going through I1, you just have to figure out what is the resistor in the I2 branch, which is just now the complicated formula that we derived. Now, if you want to figure out the current going through I2 branch, then you just have to figure out what is the equivalent resistor going through I1, which is Ri. So that is exactly what we are doing. The total resistor is basically Ri plus this resistor that we derive, which is equivalent to the resistor going through I2 branch. And then since I'm obtaining I1, so I take the resistor at the I2 branch. This is the I2 branch resistor. This is how I obtain I1. And then to obtain the I2, again, this is the total resistor, but I replace the numerator with the I1 branch resistor. Okay? And then the VR, same thing, total current beta I1, subtract away I2, and then multiply by RL, you add the negative sign. And I1, I2 are already derived, so I just have to substitute. Again, very complicated, but conceptually, the derivation is usually quite simple. And of course, we need to manipulate algebraically. After you do that, okay, again, same thing. Ri usually is a few K, so if I have decent R multiplied by the beta factor, I can ignore this guy. So same thing, decent RL multiplied by beta factor, so all this thing is going to be small. So eventually, everything cancels out. You end up having same thing, minus R. So approximately, for trans resistance amplifier, the gain is always determined by the feedback register. The derivation is very complicated. Do I need to test you all this derivation again? No. But the important thing is the result. So now you know what is the equivalent RE. So R plus RL divided by the gain. That is how I will remember, right? So for example, R plus RL, and this is the amplifier gain. That is how I will remember. Okay, how about the RL? Okay, RL I think you can derive on the spot. Okay, and then the gain is basically just the feedback register. So we go through all these derivations just to show you what this is. So this register is very popular for optical communication. So next time if you want to use it, you will know how to do. And you'll probably say, why not using the OM? Minus A, I can use the OM to create the gain. Now remember this, when we talk about optical, these are very high frequency. We are talking about 100 of gigahertz. Okay? So RM usually limited to what frequency? 100 megahertz. Right? So therefore, you can only use very simple structure, single transistor amplifier, so on and so forth. And then you feedback it. Otherwise, the parasitic is going to kill everything. Okay? So for optical amplifier, that is very high frequency, that is what we do. Now, low noise amplifier, you probably heard the term. This is a very popular term for RF. You know, engineers always like to invent something to scare people or trying to make themselves sound professional, right? So, low noise amplifier, simply put, single transistor amplifier. That is all it is, right? But why they add the low noise? Because they want to emphasize the key thing. The key in this amplifier design is to make sure noise is minimum, low noise. So therefore we call it low noise amplifier. And why is target for RF? We'll talk about cell phone. Cell phone transmits signal from base station all the way to your mobile phone. The signal that you're going to get is probably in microvolt or 100 or tens of microvolt or 100 of microvolt, very small. And if you're not careful, your device noise is going to kill it. So therefore it's very important for you to minimize the noise of this amplifier. Okay? There are some very popular way of designing the RF amplifier. I think I mentioned this. For RF amplifier, important thing is impedance matching. Right? Your antenna is 50 ohm. I want to design amplifier that actually present 50 ohm impedance match. Why we need to do that? Because antenna is like a power source. It actually extract power. Okay, the radiation power. Now to extract maximum power, you want to have the impedance match so that you can get maximum power transfer. That is the reason. Okay? But a simple way is, I just put a simple 50 ohm resistor at the input. That would be the simple way. But any resistor that you introduce always got noise. Okay? There is no such thing as noiseless resistor. Okay? When you have resistor, there is always noise. Do you know why? Resistors, think about it. Okay? You want to resist. You want to fight against something. When you fight against something, you always create noise. Right? Simple as that. But to be put, the physical origin is the reason there is a resistor. When the electron travel, they don't travel in the smooth path. They just go everywhere. So they bombard with different atom, other thing. And all this create noise. And the noise component, usually people just use a simple thing, 4 kTr. So the larger the resistor, the larger the noise. So if you use a 15 ohm resistor, the noise is fixed. You are going to live with this kind of noise. So that's why common gate or common base amplifier is popularly used. Because for common gate or common base amplifier, okay, let's say this is a current source and the antenna is here. You look into here, what you're going to see, the resistance is 1 over Gm. You can tailor this guy to make that equals to 50 ohm. But this resistance is not real resistance. This is what we call fictitious resistance. It gives you a number, 50 ohm. But is it a real physical resistor? No. It's a characteristic of the transistor. It just happened that if you use this transistor in this manner, when people look into the source terminal, it gives you an equivalent 50 ohm. The noise is not zero, but it's better than right away you use a 50 ohm resistor. Okay, so common gate or common base amplifier is a very popular way of designing RF amplifier. Okay, it's straightforward. It's so straightforward. I don't have to cover it. Okay, here we cover another type called inductive degeneration. Inductive degeneration, LNA, low noise amplifier. The principle is the same. So about low noise amplifier, the key thinking is that how can I create 50 ohm without real resistor? Okay, it's like a blank, how do I say it? It's like you are telling people, my company is very strong. I got $1 million, but that $1 million is not real. Okay? So something like that. It's not cheating. It's not cheating. But in circuit, that is how it is. So let's take a look. How can we create a 50 ohm real part without a real register. Interesting. So look at this architecture over here. Let's forget about this at the moment. Let's forget about this at the moment. If you look at this amplifier, this is actually common source. The input connected to the gate. The output coming out from the drain. The source terminal, not to the input, not to the output, so common source. But the source terminal is not directly grounded. In fact, it's connected to an inductor, so therefore we call it inductive degeneration. Inductive degeneration. Now to derive this, it is going to be very, very tedious. So I'm going to borrow what we have learned when we derived the reflection rule for BJT. We learned about this. In deriving the BJT, if you look into the base terminal, the equivalent resistance, Rx, is given by what is the transistor resistance, which is Ri, right? And then added this additional thing, Re, boosted by 1 plus beta. And if you sort of re-manipulate it, you'll see that it's given by this guy. Because beta can be further decomposed into GMRI, so something like this. Okay? So, based on the BJT, I can actually split into 3 components. We derived this result before. Remember, MOSFET and BJT, they are very similar. Here, the only difference is that BJT has RI. MOSFET doesn't have RI. But at high frequency, although you don't have RI, you do have something similar to RI. You have CGS. Okay, and what is the equivalent impedance for this CGS? 1 over SCGS. Okay, so I can actually do a one-to-one mapping. So if BJT telling me I want to find the Rx, what I can do is I figure out what is the resistor across base emitter junction, which is Ri, and then I add Re, and then I add GM Re. So I do the same thing, do a one-to-one mapping, except that now I don't have Ri. I have this guy instead, Zi. And I don't have Re, instead I have Zs over here. So let's do one-to-one mapping. So the first term is Ri, so I replace it with Zi. The second term is Re, so I replace it with Zs. The third term is Gm multiplied by Ri multiplied by Re. So the last term is Gm multiplied by Zi multiplied by Zs. Okay? So this is again very smart way of looking at circuit. I don't have to go through the whole derivation, hybrid pi model, and then trying to derive everything. I borrow the concept. We have done the BJT, we go through that, and we got the result. So now it's just a matter of mapping. Now what does that bring us? If you design RF, you will know. This will present positive reactance. This will present negative reactance. Agree? Now this positive, negative reactance, usually you will try to design such that they cancel out at the desired frequency. And what is left is this guy. This guy is not complex number. There is no frequency component. You only have GM, you only have L2, you only have CGS. But you realize the real part. Agree? It gives you the real part. So it gives you a way to map or to match 50 ohm, the real part. But it's created from what kind of component? Inductor, noiseless. Right? Capacitance, noiseless. So they are creating a real part from a noiseless component, not from a noisy component like resistor. So therefore this structure is a very famous low noise amplifier structure. We call it inductive degeneration, low noise amplifier. Okay? So the key idea, using some noiseless component to create a real component, a real part, okay, to match the 50 ohm. So of course we can go through the derivation. This is only the Zx looking into the gate. So here you look at the structure, we still have the Rg, we still have the L1. You're probably wondering what is Rg. Now, if you look at the transistor, usually we say looking into the gate, resistor is infinite, we don't care. But when you have RF, that is a different story, right? When you lay out the resistance, lay out the gate, actually the gate has a resistance. Okay? This resistance depends on how you lay out. Did I mention in the first lecture? I do, right? Multiple finger. Can you recall the example? The first lecture? Even I can't remember. I thought I did the... Oh, I didn't? Huh? I didn't mention this? I thought there is a number of resistance.
But you mentioned the fingers, but you didn't mention.
Okay, never mind. Okay, so this is to explain why there is this RG over here. Now, when you lay out the transistor, so this is the gate, this is the source, this is the drain. Now, this gate resistance is not zero, it's there. In normal analysis, we don't care because we know that you're looking into the gate, you get infinite, so you don't care. But when you talk about RF, there is a different story. You do care. Okay? Why? Because if you look at this guy, there is a resistor, which is this guy, RG. And then when you have the capacitor due to the gate, now you will form a RC, low pass. So that will affect the frequency. So this kind of single finger transistor usually is not good. So what we want to do is, for example, if you split it into two finger. Okay, so suppose this is W. So this is half W. So this resistor, if this guy is RG, so this resistor is going to be half RG. Half RG. But don't forget, this has to be connected in parallel because we are forming the gate. So effectively, you are going to have half RG parallel with half RG, going to get 1/4 RG. So by splitting a transistor into two finger, you effectively make the effective resistance 4 times smaller. The more finger, the better. So usually there are some rule of thumb. So for RF, usually we don't try to make a finger width bigger than 2 micron or 5 micron, depending on the frequency that you're operating at. So we use multiple finger. But no matter what you do, you always have this RG. The only question is whether it is big or small. And this RG is real resistance. Real resistance. So which means it contributes to noise. But if you make it small, let's say it becomes 10 ohm. Or you can make it even smaller. You make it 5 ohm. And then the rest of the 50 ohm coming from here. Then you can create a lower noise 50 ohm match. You get the point? So the effective Z-in is going to be given as this guy, SL1, and then the RG, and then this guy, and then followed by this guy. Now you look at these two components. RG is real physical resistance. It contributes to noise. The last term is fictitious resistance. It doesn't contribute to noise. These two combined give you the impedance match, 50 ohm. Okay? So your job usually is minimize RG, maximize the last one. Then you can create lower noise. Then how about these two? These three? Again, we try to cancel out. 2 of them provide positive reactance, 1 of them provide negative reactance. So you will try to create such that they resonate out and give you 0. Okay? So that is how we treat the Z-in. And then in terms of the GM, so if you look at the GM, you will see that we actually have a bunch of total resistance, which is given by this denominator over here. And across all these things, only this component contribute to VGS, the gate to source voltage. So you put it at the numerator. Why this is important? Because only this portion, VGS, give rise to the current. all the other component doesn't give rise to current, because the current, dependent current source is what? GM VGS. Only the VGS voltage give rise to dependent current source. So we use an impedance divider to figure out how much current actually gets generated. Okay, and then you substitute. Of course, you are going to put in, you already know this guy will cancel out at the resonant frequency, so eventually you end up having something like this. Okay, so we are going to pick L1, L2 such that it resonates out with CGS, and the resistance now got physical one and the non-physical one, and our goal is trying to make them equals to 50 ohm. So this is a very famous example of low noise amplifier design, single transistor. It look a bit complicated, but again, we just make use of the driving point concept. What is the disadvantage of this low noise amplifier? It sounds wonderful. You create 50 ohm without any noise, or very little noise. What is the drawback? Area is one thing. Inductor is always area intensity. Okay, good, one point, area. What else? Power, not really. Power, not really. You can play around with the factor. Bandwidth. This is actually narrow band design. If you think carefully, this is actually narrow band design. You look at, you only work at one frequency. Am I right? So at other frequency, it actually doesn't work that well. So you only work one frequency, and therefore, it's a narrow band design. So for this kind of amplifier, nowadays, narrow band design is fine, but if you look at the RF standard nowadays, I have Wi-Fi at 2.4 gig, I also have Wi-Fi at 5 gig, right? Now, if I design narrow band LNA, it means I will need 2 amplifiers. Agree? But that is not good. It means I need 2. What if I create an antenna that can take in 2.4 gig and 5 gig? I create one wideband amplifier, low noise amplifier, that covers 2.4 gig and 5 gig. So it doesn't matter whether it is 2.4 or 5 gig, I receive everything. Okay? So narrow band amplifier has their limitation. You can sort of improve this guy a little bit. If you think carefully, there are 2 resonant. Can you tell me where are the 2 resonant? Where are the 2 resonant? I thought it's quite obvious. You cannot see there are 2 resonant. You know 1 over square root LC always give you resonant, right? As long as L and C always resonant. So where are the 2 resonant? This is one of them. And? This is another of them. Am I right? So if you just rely on one of them, you get narrow band. But what if I have this kind of resonance? That is for the input. This one, I get another one, slightly shifted. You combine them, you're going to get something like this. Am I right? So this is a very popular technique people call staggering. Stagger tuning, right? Stagger resonance or something like that, staggering. So basically, the resonance, shift a little bit, make it wideband. Now, of course, you cannot shift too much. If you shift too much, then it becomes something like that, dual peak. Okay, so it requires extensive simulation, and sometimes you might need to tap out to make sure that it works. Fine-tune it, and then eventually you stick to it. The good thing about LC is that inductor usually is quite reliable, plus minus 5%, but capacitor can change. But in order to cater for it, you can always use variable cap or capacitor back. So if it's off, try to tune it back. So you always get sort of wide band, something like the green one over here. You can make it slightly wide band, but it's still not as wide as from 2.4 gig to 5 gig. That is ridiculous. Okay? So here we look at another simple low noise amplifier. So just to show you, even what you learn, common source amplifier, a very simple single stage amplifier. people can publish paper. To be frank, single stage amplifier is not new. Circuit has been invented since 1930. This paper published in 1996. That is 60 years later. Okay? But if you look at it, the architecture is fundamentally common source amplifier. So let's take a look. So at first glance, wow, this is crazy. So many transistors. So if you are IC designer, the first thing you do, break down. Okay, break down. You know that RF input comes from here, output from here. This is probably some auxiliary circuit. Okay, let's forget it at the moment. We can look at it later. Okay, now this looks like a current source. Okay, this looks like some biasing. So this is basically just to provide a resistance so that I will not right away get very low 1/GM equivalent resistance. Now this is the common source amplifier. But this has a particular name. People call it current reuse. Now why people call it current reuse? If you think carefully, the same current go through the PMOS and NMOS, am I right? So that is current reuse. Now NMOS itself is actually a common source amplifier. PMOS itself is also a common source amplifier. So you are creating two common source amplifiers using single current. Think about that. If you want common source amplifier, usually you will do this kind of thing, right? So there is a resistor here, there is another resistor here. So probably connect them together, and then this is the output joined together. Something like that, right? Usually you will do that. But that will create two kinds of current. This will consume one current, this will consume another current. Now this is ground, this circuit is actually separated. So you can create two common source amplifier, but you have to consume 2 times the current. Right? But what this guy is doing is just simple usage of PMOS and NMOS. We are able to create 2 common source amplifier stages by reusing the same current. Okay, so the total LNA current, according to the paper, is 7.5 milliampere. So here I'm just trying to break down, because usually people don't give you the detailed design step. So here I'm just trying to show you. We can actually reverse engineering. If you know what you're doing, reverse engineering, based on some information given, you can actually figure out what is the final sizing that is being chosen. So according to the paper, total LNA current is 7.5, but they have 2 stages, meaning that this is one stage, followed by another stage. So if 2 stages consume 7.5, so just this stage alone should only consume like half of it. So that means 3.75 milliampere. So we need to decipher the paper. So here, the paper didn't give you more detail, but we can sort of trying to do some power budgeting. So as an IC design, we do power budgeting. What is power budgeting? You have different branch, so you have to think how much current to assign to which branch. So of course, this is the amplifier branch. You want to reserve most current to it, right? Because amplifier branch is the one that's doing the hard work. It doesn't make sense that the guy bringing $1 million to the company, you pay peanut. And then the guy who only bring in $1,000 to the company, you pay $1 million. It doesn't make sense, right? So if you look at the thing, you know that this is biasing, so probably doesn't need that much current. Okay? This is the one that's doing the hard job. So I need to give most of the current. Now this, I didn't talk about that, but that is actually trying to establish the biasing as well. So we can consider it as some existing circuit. So again, it helps, but it's not the main function. So we will assign some current. So here is arbitrary, depending on how you want to assign, but I like nice number. So 3.75 milliampere, right away I think, let's give 3.5 to the main amplifier. Okay, then I left with 0.25. 0.25, I have 2 helping circuit. The first branch, so simple, give him 50. And then the second branch, a bit complicated, give him 200 micro. I'm not saying this is the right way. As a designer, eventually you have to make decision. Okay? I always tell students, as a designer, you don't have to think whether your answer is right or wrong. You just need to be able to justify. Justify means that you stand up here, your engineer team asking you, why do you do that? Why do you give 3.5 milliampere to the main amplifier? If you are able to stay firm saying that, 3.5, nice number, and major of it is the major current consumption, I give it to all to the amplifier. But who say that 3.5 is the best? Can I do it with 3? Of course, why not? How about 3.7? Why not? Right? So there is no right or wrong answer, just able to justify. Now, of course, you don't stand here and say, I decided to give 0.5 milliampere to the amplifier, and the other 3.25 all to the other circuit. You will not be able to defend yourself. It's like you're trying to justify giving $1 million guy $1,000 and giving the other guy that only bring in $1,000 million. How can you justify yourself? So as long as you're able to justify yourself, it is fine. And then according to the paper, every stage will give you about 15.6 dB. That turns out to be a gain of 6. A gain of 6. And these are just some of the parameters that I extract for the, I don't know the technology. I think it is 0.6 or 0.35 micron. Okay, something like that. Now then, there are some other auxiliary circuit that we need to care about. You'll see a lot of resistor and capacitor. Okay, the CB, RxCX, for example. Now, before we move on further, this RxCX you already know. This is low-pass filter. Why do we need this low-pass filter? You know the output is going to be a RF signal. Now, this RF signal pass through this low-pass filter, mainly trying to extract the DC. You get the point? It's trying to extract the DC. After you extract this DC, it's going to compare with another desired DC, VB. And this output is going to feed back to adjust this amplifier that will affect the final DC point. So if you think carefully, this looks very much, if I consider this guy as a amplifier, okay, this is VB, this is the after filtering, going to here, and this is actually adjusting this current source. So you know for negative feedback, eventually, due to the virtual short, the DC of this guy is going to be exactly equal to VB. Am I right? So this technique is using the negative feedback to establish what is the final DC that you will allow for this RF circuit. So if this DC go higher, it will feedback, trying to bring this guy down. If this DC go lower, it is going to feedback and try to bring this guy up. So due to this negative feedback, you are going to establish the DC biasing to exactly what you want, VB. So that is what this circuit is doing. So if you understand this, then this is basically doing the low pass filtering. So that helps you to select what should be the RC pole. Now, how about this CB? This CB is actually a common source amplifier. If you think carefully, without this CB, this will present as a resistor. Then what you have is actually a common source with degeneration. Am I right? Common source with degeneration, the gain becomes GM1 plus GM-RE. So it's going to drop. You don't want that, right? So in order to make it small, you need this RE to go to 0. That can be done if you insert a capacitor. Because in capacitor, if the frequency is high enough, it's short circuit. But you know, the CB cannot be 0. You just have to pick the CB big enough so that it's close to 0. How close is close to 0? How about 1 ohm? You make it 1 ohm, it's very close to 0 already, right? Come again? Huh? 1 ohm. 1 ohm. Because the capacitor impedance for CB is given by 1 over j omega CB. And your frequency is 900 megahertz. So you just need to make sure that at 900 megahertz, this CB presents as a 1 ohm resistance. So having understand that, that is what we are doing. So CB at 900 megahertz, I want to make sure it becomes 1 ohm. So the CB is about 176 picofarad. 176 picofarad. Now, this CS and RB actually form a high pass corner. If you think carefully, this is CS, okay, and this is RB. So this is actually high pass filter. So high pass corner, your band of interest is at 900 meg. So as long as you pick CS and RB, 1 over CS RB divided by 2 pi to be much, much smaller than 900 megahertz, you're okay, right? And since CS is at the input, this capacitance can be easily put outside the chip. Okay, so I just pick CS equals to 1 nanofarad. And then RB, I make it becomes 100 kilo ohm. Okay. So the low frequency cutoff is 1.6K. So I still make sure the band is actually wide enough. Now CB we already covered. And then make CX the same so that at 900 megahertz, the amplifier only see RX. What do I mean? So if CB and CX are the same at the frequency of interest, this guy is just ground. So your Vout only see RX. Vout only see RX. That is what I mean. So CS is external, CB and CX is non-critical. You don't want to put so many capacitors outside. So CS makes sense because it's right away before the input antenna. So I can put there externally. Now CX CB, if you think carefully, 176 picofarad is not small. It's not small. So typically we would like capacitor to be below or around 20 picofarad. Okay? 176 is quite extensive. But this capacitor is not that critical. Not that critical. So if it's not that critical, I don't need to guarantee the accuracy. I can pick the highest density capacitance, which can give me 10 to 15 femtofarad per micron meter squared. The best capacitor, Morse cap. Okay, so I can use it. So I'm going to use Morse cap to give me, and according to this result, the area is not that extensive, about 195 micron by 195 micron. Okay, quite small enough. If you talk about other capacitor, I think the maximum is 4 femtofarad. So this area is going to be ballooned up by probably 4 times. Okay? Now then we need to determine the 3 dB bandwidth of this amplifier. So for this amplifier, I need to make some decision. Okay? So again, it doesn't mean what I do is correct. So you can do some variation on your own. I do some rough estimate because my amplifier is going to drive another amplifier. So the another amplifier is going to show as a parasitic capacitance. So that parasitic capacitance could be quite significant because depending on the sizing of the amplifier. So I just do a rough estimate 500 femto. So again, design is not like one hit. You have to come up with some number. If it doesn't match, do iteration. If you overestimate 500 femto, next time you make it smaller. If you underestimate, next time you make it larger. And then adjust your calculation accordingly. So here I just do some rough calculation, so probably about 500 femto. And then I want to design the amplifier up to 900 meg. I don't want to design exactly at 900 meg. I want to give some margin. Right? So as design, usually you provide some margin. You don't want to design tightly. People want 900 meg, you give 900 meg. Okay, people want 900 meg, you overshoot a little bit. Okay, when you overshoot, when you didn't meet, you will still be able to meet. You get the point? Aim high, when you shoot low, you still end up decent target. That is the reason. So instead of targeting for 900 meg, I try to target for 1.5 gig. And that turns out the RX is about 200 to 300 ohm. Okay? So with that, I can start analyzing the circuit. Actually, the gain is quite straightforward. I already tells you this is 2 common source amplifier. One common source from the PMOS provide you GM and P. One common source provide you GM and N. And these 2 outputs sum together. So the 2 GM sum together. And what is the total output resistance? You have the output resistance presented by the PMOS, R0 MP. You have the output resistance presented by the NMOS, R0 MN. And you have the parallel resistance RX. But eventually, this is going to be much bigger because this is only 200 to 300 ohm. So you can ignore it. Okay? And therefore, you lump GMN and GMP together to become GMT. And you know already your target. I want to get a gain of 6. So from there, with the RX of 200 to 300, I can get GMT of 20 to 30 milli. And therefore, PMOS and NMOS should be around 10 to 50 milli. So based on this understanding, I work backward. Okay, I already know what current to assign. I know the mu n COX. I can then figure out what is my W over L. And it turns out with this simple calculation, this sizing turns out to be exactly the same as what the paper has published. Okay, so that is how you reverse engineer to see what is going on. And then for the other transistor, because it's current mirror, so the sizing is directly related to the current ratio. So if you already pick MP2 to be this sizing, then MP1 can be obtained accordingly. Okay? Then we have to figure out the biasing. So for the PMOS current, we already allocate 3.5 milliampere. You can figure out what is the corresponding voltage, and that gives rise to the DC voltage for the VA. And similarly, with the NMOS, you can figure out the VGS, and with this VGS, you can figure out what should be the VCB voltage. So what is this voltage? You look at the circuit. This is the VA. VCB is basically here. VCB. And of course, after you go through all this analysis, you want to make sure all transistor is in saturation region. So the current source that you design, you better make sure it's smaller than the available voltage. Okay? So with this one, you can end up having the sizing for MN2 as well. And the rest, so this is again trying to do some current mirror ratio. So here you can see that this guy is mirror from this guy. They are actually current mirror. So with this current mirror, you already determine the sizing for this one, and the current is 3.5 milli. The current here is about 100 micro, because the total is 200 micro. So you can determine the current ratio, and therefore the relative sizing between these two. Now, this doesn't tell all the story. It still didn't give you an idea how to design this op-amp. How to design this op-amp over here. Now remember, do you know why for op-amp, due to the feedback, the V plus is approximately equal to V negative? Do you know why? Because virtual short mainly because the loop gain is big. Because the loop gain is big, so that it forces the difference to be very, very small. So the key is actually the loop gain. It needs to be much bigger than 1. What is the loop gain here? If you start from here, so you go through this guy, and then go through this amplifier. If you look at this amplifier, we are going to cover differential later, but if you look at this guy, it's basically GM MP3 multiplied by this guy, 1 over GM MN3. But that is not the full gain, because once you get this guy, you are going to see GM MN2 multiplied by this guy, 1 over GM MN1 multiplied by this guy, GM MN1, and then multiplied by this guy, which is RX. Okay? And actually, if you look at this guy, cancel, and look at this guy, this is actually very similar to the amplifier gain, which is about 6, quite big. Okay? Bigger than 1. So you just have to guarantee this is also bigger than 1. Then you can guarantee the loop gain is actually bigger than 1. So therefore, that is what we do. We just make sure these two multiply together bigger than 1. Since we already select this sizing, so after going through this expression, I can also determine what should be the MN3 accordingly. Sorry, MP3 accordingly. Okay? So of course, all this is ballpark calculation. Nothing is accurate. So once you got this calculation, you put it into the schematic and simulate. Okay? So once you simulate it, you will start to adjust. For example, you find that, okay, for this amplifier, the gain about 15 dB, pretty close to what I want. The bandwidth also close to what I want, about 900 meg. Okay, it seems like I probably don't have to do anything, but if it's short, then let's try to adjust. Maybe I try to lower the resistance, pump more current, or trying to get the resistor larger, okay, make the capacitor smaller, so on and so forth. So you can try to fine tune, but this basically gives you some ballpark figure how to calculate to actually get what you want. Okay, so all the previous example is trying to show you even single transistor amplifier can be quite interesting. Okay, people use it for RF amplifier. And what we use doesn't exceed what we covered last week. We covered the driving point, we show you how to derive. All has been covered. But if you apply it to the RF amplifier, there are more things to consider, but fundamentally they are the same. Okay? Now, differential pair. Shown over here is the BJT differential pair. Differential pair is a very important building block for circuit. So let's look at it in detail. There are some desirable characteristics. First, insensitive to common mode signal. You will come to view clearer. What do I mean by common mode signal? Very easy to bias. Basically, we just provide a current source. Okay? That's it. Doesn't have even harmonic. That will become clearer to you also later. So here, we first go through the analysis assuming something. The two transistors are perfectly matched. The two resistors are also perfectly matched. Now, the output current basically is determined by the difference between the collector current of these two transistors, IC1 and IC2. Now, you can derive the IC1 based on the BJT equation. So you can see that IC1 is related to VBE1. IC2 is also related to VBE2. Now, the sum of IC1 and IC2 is actually given as constant current source, the TEL current source. Okay, we also call this guy TEL current source. And if you take the ratio, okay, if you take the ratio, then it becomes the IC1 divided by IC2, but you know at the exponent, if you divide, it becomes subtraction. And this subtraction, VBE1 minus VBE2, turns out to be input voltage, VI. Because one side is VI over 2, the other side is negative VI over 2. And after some algebra manipulation, okay, it's actually quite straightforward. If you do this guy as IS exponential VBE 1 over VT plus IS exponential VBE 2 over VT, okay, that equals to EE. And then you try to consider this guy as, I think, half VI. This is negative half VI. And then doing some algebra manipulation, you end up IC1 given by this guy, IC2 given by this guy. And the output current, since it's given as the subtraction between the IC1 and IC2, you end up having this hyperbolic tangent function for differential pair. Hyperbolic tangent function. So what does hyperbolic tangent function looks like? It looks like something like this. Hyperbolic tangent. It's not that difficult to understand. If you look at the circuit without looking at this guy first, you have a constant current source. So if one side is higher potential than the other side, the current will prefer to switch all the way to the other side. Okay? On the other hand, if this side is higher, then the current will prefer to go all the way to the other side. So when you go to this side, because you use IC1 minus IC2, you have the fixed positive IEE. Now, if all the current switch to the other side, you have IC1 minus IC2, you are going to have negative IEE. So that is what you are going to get. IEE, negative IEE. Now, in between is where it is switching. And this function is well described by hyperbolic tangent. Hyperbolic tangent, we are going to derive the gradient. Because the gradient is going to tell you how much the current is going to change with respect to the input voltage. Okay? This is x-axis input voltage. This is y-axis output current. So finding the gradient, delta I naught over delta Vi. It's basically taking the hyperbolic tangent and then trying to do the derivative. turns out to be hyperbolic second square. So that is the well-known derivative. And if you substitute, because we're only interested at this point, the maximum gradient, so that is happening at Vi equals to 0. So it turns out to be this constant term over here. And that would be the Gn for your BJT differential pair. BJT differential pair. Now, the hyperbolic tangent function is actually this guy. And you can expand this guy using the Taylor series. After some algebra manipulation, okay, the numerator becomes like this, denominator becomes like this. You bring the denominator up and then try to expand them. Eventually you see they only have odd term. They only have odd term. That's why we say differential circuit only have odd harmonic. What do I mean by odd harmonic? You try to put cosine omega t. So your input x is cosine omega t. This circuit is going to generate cosine omega t to the power cube. But cosine omega t to the power cube, you know eventually they can be converted into cosine 3 omega t, third harmonic. Okay? So same thing, you have x to the power fifth, that is cosine 5 omega t, fifth harmonic. So ideally, the differential pair only exhibit odd harmonic. Odd harmonic. Harmonic is something undesirable. In fact, what we want is basically just cosine omega t. Think about that. If you have a sine wave after amplified, you should only expect to get sine wave. If you get more than sine wave, your output is being distorted. Okay? So you want the harmonic to be very, very small. So if you use a simple common source amplifier, the harmonic that you are getting beside fundamental, you are going to get even harmonic and also odd harmonic. So one thing good about differential circuit is right away it helps you remove all the even harmonic. You only have odd harmonic. Okay? But that is not the full story. The reason we didn't see any even harmonic is because we assume Q1, Q2 perfectly match. Okay? R1, R2 perfectly match. If they don't perfectly match, you're not going to get this very nice term. Okay? There will be some residual. They don't cancel out. So usually the even harmonic is limited to minus 30 to 40 dB. Why? Because the transistor matching, usually the best you can get, not the best you can get, a very easy way that you can get is about 1% matching. 1% matching. 1% happens to be about 40 dB. Now if you want better than 1%, the transistor size has to be bigger. Okay? And sometimes trimming is needed. Same thing for the resistor. So in IC design, usually 1% is considered quite easily doable. Okay, you don't have to pay too much attention, quite easily attainable. Now, in differential circuit, if you try to analyze the gain, one thing that we would apply is the so-called half circuit concept. Half circuit concept. So if you look at this circuit over here, now, what is the concept of AC ground? We said DC voltage is AC ground, right? Why? Because the voltage doesn't move. So in the AC analysis, if the circuit doesn't move, it might as well be ground. That is why we consider DC voltage to be AC ground. So if you try to extend this concept, if you find any node where the voltage doesn't move, it can be considered as AC ground. Am I right? And this is exactly what happened for differential circuit. If you look at the differential circuit, the way they move is always like this. When one side go up, the other side go down. Right? It's always like this. So it's like a seesaw. Now, if it's like a seesaw, this happens to be at the middle point. Am I right? So when you move up or move down, this point happen to be at the middle point, never change. So if it's never change, which means it's constant, so it can be treated as AC ground. So when you try to analyze the differential circuit, you can apply this kind of half circuit concept. So you see that this current source actually is useless because it doesn't move. So I can just consider this circuit, but the emitter is exactly grounded, AC ground. The other side also the same thing, grounded AC ground. So this analysis simplify into a simple common emitter amplifier. We've gone through this, am I right? So the gain is easily done. The RID for half of them is about RI, but you have another half that is RI. So you combine the two in series, therefore you get 2 RI. For the output resistance, same thing. If you look at this guy, is R1 parallel with R0, but that is only half of it. So you have 2 of them in series, so therefore you have 2 of them. Okay? In terms of the gain, so this guy will provide you the GM cell, and then it will multiply by the total register, this guy. Okay? Why there is no 2? Because every one of them only contribute half. But if you add together, because your input is only half, so if you consider the output is basically just half GM R1 parallel R01. But because you have 2 circuits, so you multiply by 2. So it turns out the 2 cancel. That's why you end up having exactly the same as common emitter amplifier. Okay? Now here we want to talk about common mode. So in differential pair, we always input the signal like this. We use a differential signal. Okay, we do it like this. And then we observe the output is also differential. Okay? What is common mode? Differential means the signal always do opposite thing. Common mode means the signal always go up, go down in the same way. That's why we call it common signal. Okay? So if they are the same, you can see that the way I model the signal, I use exactly identical voltage source. Now, can I still use the half circuit? You can. But here, the middle point is no longer AC ground. Because if you think carefully, if I move up and move down together, the middle point, does it change? It does. It go up, go down together also. So therefore, you cannot consider this point as ground. Now, we can still use the half circuit. The way we think of it is, the current source, because the two are identical, so the current source I can split half-half, right? And you know current source is not ideal, so the current source also have output resistance. Now the resistance I also split half-half. When combined, you are having 2 combined in parallel. So if you split, each of them should be twice larger. So therefore, if you split it, the current is half smaller, but the resistance is actually twice larger. So using this half circuit concept, we can analyze the circuit in an easier manner. So we can see that the VOC over 2, the output due to this input, we already derived this guy. This is actually common emitter with degeneration. So the gain can be easily found. This is the GM. Okay? GM divided by 1 plus GM, the register is 2RE. So therefore you have this guy, 2RE. And then you multiply by this register R1. So this is the so-called common mode gain. Common mode gain. But for differential circuit, you have to ask yourself, am I interested in single-ended output or differential output? These are 2 different concepts. Single-ended output means that I only look at one side. I don't care about the other side. That is single-ended output. Now differential output means I take the difference between these 2 outputs. That is differential output. Now, if we are talking about ACM, single-ended output, we can just use single ACM, that will do. And that is what we derive. Okay? That is what we derive over here. More interesting is actually the differential output. So, if your signal move together, you measure the output difference. What will be the effect? If you think carefully, if you move like this, one side go this way, the other side also go this way, they go simultaneously, right? So if you subtract them, the output should be 0. So ideally, the common mode to differential mode should actually be 0. That is one of the desirable characteristics for differential circuit. Why? If you think carefully, why all the RS circuit engineer, all the analog IC designer always tells you, we prefer to work with differential circuit. If you ask them, they always tells you, we prefer to work with differential circuit. Why? common mode gain to differential mode is 0. Why that is important? If we talk about power noise, very likely the power noise will appear at the two input in the same manner. Am I right? So the power noise will actually appear as a common mode signal to the two differential input. So if the power noise move together, you look at the output also move together, but you take the difference, 0. So the effect of power noise on the differential circuit is 0. Right? So that is the beauty. Supply noise doesn't matter. How about normal noise? Now, if you think about normal input noise, you also have this kind of characteristic, because let's consider here, right? These two persons, very close. The noise source is from the acorn over there. When they have the close proximity, the noise source from there reaching both of them should be quite identical, right? So the circuit is the same thing. A lot of time, a common noise source, when they appear to these two differential input, they appear to be the same. So if you're only looking at one single output, the noise will appear. But if you look at the differential output, because they appear the same, they cancel out, 0. Why signal input doesn't get affected? Because the signal moves like this. They don't move identically. They move differentially. So when they subtract the output, they don't cancel out. So that's why in analog and RF circuit, a lot of time we prefer differential circuit. That is the reason. Okay, that is the reason. Now, that's good. But you know, that is not the whole truth. Although, if you have perfectly matched circuit, you are going to have infinite common mode rejection ratio. It means 0 common mode gain. But if you look at any mismatch, so let's go through the derivation. Supposedly, your GM, okay, consists of this GM1 is slightly larger, this GM2 is slightly smaller. So when you combine them, you actually get 2 GM. Okay, so actually at the bottom one, this GM is still the same. But if you look at the top one of the common mode gain is going to have slightly larger GM, slightly larger resistor. The other guy, so this path refer to this guy, this path refer to this guy. Because of the mismatch, the other guy will have smaller GM and smaller R. And then now if you try to take the difference, now the delta will show up. And if you try to manipulate it, still take out this very well-known term over here, you start to see the common mode to differential mode gain actually depends on the mismatch. If there is no mismatch, let's say delta M becomes 0, delta R becomes 0, you get 0. But let's say you can only get 1%. You can only get 1%. It doesn't mean 40 dB, because this is still very small. Okay, so you go through the calculation here. So you can see, if you are talking about single-ended output, so in terms of the differential signal, your gain is half. In terms of the common mode signal, you get this guy. And common mode rejection ratio is basically defined as the differential gain divided by the common mode gain. So the differential gain is half AD, common mode gain is ACM, so you end up having this guy. If you are talking about differential output, then your output is the gain due to the differential signal and the gain due to the common mode signal. And the common mode rejection ratio, AD over ACMDM, is given by this equation. You simply put in some value. So GM equals to 1 milli, RE 100K, typical, and mismatch of 1%. You can see that single-ended output give about 40 dB common mode rejection ratio. But the differential output actually give 74 dB common mode rejection ratio. So that actually highlight to you the usefulness of differential circuit. Okay? And the principle is like this, very simple. When they move equally, they cancel out. You don't have noise. Okay? That is the beauty of it. So remember, all the analog and RF designer, they always like differential. Here is what I'm going to talk about. If you think about that, if the signal moves differentially the same way, then actually, as long as I have two identical circuits, I move equally, okay, I should have very good common mode rejection ratio, right? So I've shown here, this is the differential circuit. We call it differential. This is what we call difference circuit. They look quite identical, am I right? Except one got current source, the other don't have. Right? Okay, so they are the same. Quite similar, not the same. Now, if you try to analyze this circuit we're already going through, and the common mode rejection ratio is about 74 dB, quite high. But if you look at this circuit, okay, the output is differential gain, so which is really quite similar. Okay, same, identical. But the common mode gain, if you look carefully, the common mode to differential mode gain is given by this guy, and then multiplied by this mismatch. It's actually missing this factor. It's actually missing this factor. And therefore, if you look at the common mode rejection ratio, it's actually not that high. It's only 34 dB. 34 dB. So this actually illustrates the key difference between differential and difference current source. Because of the current source is forcing two sides always balance out. Because when one side increase, the other side have to decrease to balance out. But in different circuit, that is not the case. Because they are independent of each other. Okay? So if you want to compare differential versus difference, differential is always better. But if you compare single-ended with these two is always better than single-ended. Okay? Why people like this guy? If this is the best, why people like this guy? Any idea? Come again? Yes, a very good point, larger range. Nowadays, the voltage headroom is shrinking. We are talking about 0.1 or 0.8 volt, 1 volt. Supply is shrinking. Okay? When you have additional current source, you actually have to allocate additional voltage headroom for that current source. And you don't have enough swing. So a lot of time people prefer to get rid of the current source. That is one reason. Another reason is like, people actually find out the current source, although is good, but might not be that effective because with very advanced technology, the output resistance is dropping. So with the output resistance dropping, actually what you get from here, the common mode degeneration is not that much higher compared to different circuit. That is another thing. Another consideration is actually you're introducing noise. Okay, this is particularly the case for VCO. Some people find that in VCO, the tail current noise actually get up-converted, becomes flicker noise, right? So that actually deteriorates the VCO phase noise. So nowadays, if you look at the circuit, people prefer to remove the current source. Although you end up having a difference VCO instead of differential VCO, but in terms of phase noise, performance is actually better. Okay, so there are multiple reasons. I'll do a stop here. We will resume 7:50. Is that okay? I still have quite a number to cover. I don't know whether I can finish today. I'll probably go a bit slower. Any question? I haven't covered sufficient material, so I'll do the poll everywhere later. I have some question prepared. Okay, we'll resume at 7:50. Or you guys want to continue? No, I'm just kidding. I see that you guys didn't move, so I thought you guys want to continue. Give me a break. I just recovered. Give me a break. 20 minutes. Thanks. Okay, let's resume. Today's lecture might drag a little bit. Just bear with me. MOSFET differential is very similar to BJT, so I probably want to do faster. Same thing, all these advantages, but let's look at how to derive the current. I out is still defined as the drain current difference, But here, the ID1, ID2 is the order exponential. You can expand the square law. The reason I split it to VB and VI, so that VB is fully constant. Okay? So actually not. Am I right to say VB is fully constant? I think so. VB is fully constant over here. Because VGC is a DC voltage. Okay? So the changes is actually split into the separate term. And then the ISS, the tel current is a constant term. It's a sum of ID1 and ID2. And after that, you can sort of manipulate and end up having the following. Then the output current is the difference, which means you expand this guy, you're going to have VB squared plus VI squared divided by 4 plus 2 VB VI. The other guy, same thing, but that becomes minus 2 VB VI. So you subtract the two terms, that's why you end up only having this guy. Okay? And then you substitute VB with the things that we derive over here. And therefore, you end up having this VI term. If you use the Taylor series expansion, so this thing you can actually expand the Taylor series accordingly. You are going to end up having also many harmonics, but they are all even harmonic, odd harmonic. Okay? And to derive the gradient, so it's basically just taking the derivative of this guy. Now, if you're only interested in the linear term, so you can see that the only constant is this guy, the gradient. Of course, this guy will give rise to harmonic term, but that will becomes like VA squared. If you do the differential, it becomes 2VI. And if you substitute VI equals to 0, okay, that term will go away. So all the higher order term involving VI will go away. So the only thing left is basically just the constant term here, which is the gradient. And that turns out to be GM1 or GM2. So similar to BJT, you always have fundamental and the odd harmonic. Even harmonic is not there. That is the beauty of differential circuit. Due to the mismatch, you might end up still same thing, having 40 to 30 dB even harmonic. For differential signal, here you notice that actually there is body effect. Okay? But if we consider like this kind of thing, seesaw, then this point is actually considered as virtual ground. And since the body is ground, source terminal is also ground, so actually they don't suffer from body effect. You can see that the differential mode, the gain is no GMB. It's actually GM. Okay? Because of this virtual ground concept. So this is the differential gain, exactly the same as common source amplifier. Input resistance is infinite because the gate, you always have infinite resistance. Output resistance is basically looking up R2, looking down R0, 2. So the two in parallel, and you multiply by 2 because of the half circuit concept. And for common mode signal, we go through the same thing. We try to split the current, becomes half ISS. The resistor becomes 2 times RSS. So therefore, the common mode gain for one side is actually given by this common mode degeneration. Common source with degeneration. And then if you assume there is a mismatch, so this guy becomes GM plus delta GM over 2. This guy becomes R1 plus delta R plus delta R over 2. And then the other guy becomes minus. Then you end up having exactly the same derivation. And we have gone through the same analysis for single end output and also differential output common mode rejection ratio. They are very similar to BJT cases, except that you have this additional minus GMB, because if you consider common mode, this is no longer virtual ground. When you split the current and the RSS, this point is not the same as the body terminal. So you always have this GMB term remain. Okay? Now, here come to an important concept called offset. In the workshop, I did talk about offset, and the way we simulate it is very simple. We just run Monte Carlo simulation. Okay, the way the Monte Carlo simulation works is this. You run the simulation, the first time, they anyhow assign Q1 to have certain IS, Q2 to have certain IS. Okay, how do they assign? They already come up with a model. When they do the experiment and measurement, they already know the IS will have a mean value for certain value, and then they will fluctuate around certain value. So all random property. So when they run the simulation, they just anyhow throw a dice, and then this one will get this value, this one will get another value. So this transistor will not be matched. And then when they simulate, that's how you end up having some offset. And if you simulate more data, maybe more than 100, you will start to see the offset emerge when you cover it more than plus minus 3 sigma. So that is how in the workshop we talk about offset. But in reality, how can we understand the offset? So the offset, using this simple example, arise due to two things: register mismatch and also the transistor IS mismatch. So when people measured, let's say the IC foundry already manufacture different transistor, they already characterized the transistor and they found all these transistors, if you try to measure their IS, okay, they will have a mean value. Okay, most of them will have the mean value surrounding here. Okay, maybe IS naught. Okay, but if you are talking about mismatch, okay, so although if there is no mismatch, let's say delta IS is 0, maybe this amount of sample will be there. But if you are talking about mismatch, you measure 1,000 sample. About 67% of the sample will fall within plus minus sigma of this. Okay, so that is what the IS mismatch is. So the y-axis is number of sample. So x-axis is basically the mismatch. So that is what this IS means. And then for the R, the same thing. If you're talking about this mismatch between the R, so you can also measure 1,000 sample of them and then figure out what is the distribution property of this register mismatch. So about 67% of them will concentrate around this value, for example. Okay, so when you have this number, what it means, 67% of the sample will have the mismatch less than 5%. You get the point? Okay, it tells you 67% of the sample. Let's say you test 1,000. About 670 of them will have mismatch less than 5%. Less than 5%. You can guarantee that. That is how they measure. Okay? And what this means is that 67% of the register sample that you measured will exhibit mismatch less than 1%. Okay, 1%. That is all it means. Now, with this guy, how can it help us derive the offset voltage? So, if you look at the offset voltage, it means what is the voltage that we need to apply so that the output becomes 0. So, the offset voltage, if everything is matched, is basically VBE1 minus VBE2, and they should be 0 because they are identical. VBE1, you can derive it, is basically ln VT IC over IS. So that is what you're getting. This guy also the same thing, but because it's subtract, so you try to flip the IS and IC. So you end up having the following. Now, if the VOS is 0, okay, to make the output offset voltage to be 0, then IC1 R1, IC2 R2 should be 0. Should be equal. Okay, that is quite simple to understand. If you want the V out to be 0, then this voltage drop and this voltage drop should be identical. Okay, should be identical. So that when they subtract, it becomes 0. And that gives rise to the relationship. It tells you, if you want the offset voltage to be 0, IC1 over IC2 should be the same as R2 over R1. And then you try to put this guy, replace it with R2 over R1. And then you know that the register, right, is going to have, let's say, assume one of them is bigger by half delta R, the other smaller by half delta R. Same thing for IS. One is bigger by half IS, delta IS. The other is smaller by half delta IS. And then we make use of this approximation. Okay. This is quite simple to understand. When you have 1 plus x over 2, okay, multiplied by 1 minus x over 2 inverse. Right? If x is very, very small, then it's approximately 1 plus x over 2 multiplied by 1 plus x over 2. Right? You know this, right? This is algebra. You just bring the exponent down. And then you expand this guy, you're going to have 1 plus x over 2 plus x over 2 plus x squared over 4, but we don't care about higher order term, so that's why you end up having 1 plus x. That's why this guy. And then ln 1 plus x approximately, the mathematician also tells you is approximately x over here. So therefore this guy can be expanded and becomes something like this. So we already know this guy will exhibit 1% mismatch, 67% of the sample. This guy will exhibit 5% mismatch, 67% of the sample. So if your offset voltage is depending on these two, all it tells you is like about 67% of them would exhibit the offset voltage of 1.3 millivolt, according to this equation. Okay? Now one thing you'll notice is like, I don't basically just put 1%, 5%, add them together. Instead, I try to take square, add them together and take square root. This is the property of random variable. They don't sum linearly, they sum in power. It's like noise, right? The noise doesn't sum linearly, they sum in power. So any random variable, they just sum in power. So you put 1% here, 5% here, and then you multiply by VT, it turns out to be about 1.3 millivolt. So that tells you 67% of the sample will exhibit offset voltage of 1.3 millivolt. That is how you calculate it. I remember during workshop, somebody is asking me, can we calculate? Yes, you can. So this is one example of illustrating how you calculate it. But it's very tedious. It's very tedious. And especially when you deal with the random variable, usually simulation, Monte Carlo simulation is probably a better way to go. Okay? Nowadays, computer is very powerful. So you just let it run overnight. So for Morse differential offset, same thing. The offset voltage is basically the difference between the two VGS. If they are identical, they are perfectly matched, they should cancel out and become 0 volt. Now to get the VGS1, you can expand this guy. This is quite easy. ID equals to half mu n COX W over L, and then VGS minus VTH squared. So therefore, you just move everything over, take the square root and move the VGS over. That's why you end up having this guy. This is for VGS1. And then this guy, that is for VGS2. Okay? Nothing tricky, very straightforward algebra manipulation. So here you can see it actually depends on the threshold voltage mismatch. So for MOSFET, threshold voltage mismatch directly appear as the offset voltage. And then the second one is actually related to the sizing mismatch. Sizing mismatch. Okay? Now, we didn't show how to calculate this one. So instead, we just tell you roughly what people normally observe is the threshold voltage mismatch probably is between 1 to 5 millivolt. And then this sizing and the mobility, all these mismatch will probably contribute to about 10 to 20 millivolt. Now, you're probably surprised. How come eventually it's not like 11 to 25 millivolt? Instead, I still consider it as 10 to 20 millivolt. Remember, random variable sum in power. So if you try to sum this guy that is between 1 to 25, this guy becomes 100 to 400. So if you sum them out, the second one is still going to be dominated. And then we take the square root, it's still going to be dominated by this guy. So that's why it's still around 10 to 20 millivolt. Okay, that is the reason. Because they don't sum linearly. So one thing to note is that for offset voltage, usually MOSFET is worse. MOSFET differential pair is always worse. So if you want smaller offset op-amp, you should look for those that are BJT. Okay? Now, before I move on to talk about current source topic, let's do some quiz. Not really quiz. There is no marks given. Okay, can you scan this? Done? Okay, which of the following is true about differential pair? So we talk about differential pair. Done? Okay. Why the first one is wrong? Why the first one is wrong? The output only exhibit fundamental and all odd harmonic. This statement, you always have to understand the context. This statement is true if there is no mismatch. Right? So if you treat this statement as always true, it means that it should be true even with mismatch. But I keep stressing this is not true. If there's a mismatch, the even harmonic will be there. So second one, I don't know why so many people choose it. The output will exhibit odd harmonic whether there is component or no component mismatch. Okay? So this statement actually implicit implies that if only when the component mismatch exists, then it will exhibit odd harmonic. But we know that is not true. Okay? It doesn't matter whether there is a component mismatch or not. Okay? I think the third one is quite clear. I already explained to you the difference between different circuit and differential circuit. Now the last one is not that straightforward. But if you recall, I stressed 2 points. Even harmonic exists if there is a mismatch. Am I right? I keep mentioning this, right? If there is a mismatch, component mismatch, there is even harmonic. So there is 1 point. When I derive the common mode rejection ratio, okay, if there is no mismatch, common mode rejection ratio should be infinity. So if there is no infinity common mode rejection ratio, it means there is a mismatch. So although I didn't explicitly tell you, this guy will imply there is an even harmonic, but these two should be linked together. Am I right? Okay, I just mentioned these two facts separately. I mentioned that if there is a mismatch, there is a even harmonic. I also mentioned there is a mismatch, CMR should be finite. So then it should come automatically. If CMR is finite, it implies there is a mismatch, therefore there is an even harmonic. Get lost? Okay? Yes means you understand, or yes, you get lost.
Get lost.
Okay, let me stress this again. You guys have no problems accepting if there is a mismatch, there is an even harmonic. Am I right? Okay, so that is quite clear. You guys also don't have issue accepting if there is a mismatch, CMR is finite. Am I right? Okay? So it means that if CMR is finite, there is a mismatch. If there is a mismatch, there is an even harmonic. Logic, right? Okay, it's not straightforward, but that requires you to link the two together. Okay, which of the following is true about the offset voltage? I don't know why the font is like that. Never mind, you can see it, right? Can you see it? Okay, good. A lot of you get it right. Okay? Random behavior doesn't mean it is not predictable. The way we predict, it also doesn't mean it's very deterministic. We cannot predict like, oh, this chip is going to be 1 millivolt. No. But we can predict if this chip is coming from the same batch, I can know that 67% of the time, this mismatch is going to be less than certain value. So this is also some kind of prediction. Weather forecast is also prediction, am I right? Can the weather station tell you exactly tonight, 10 o'clock, is going to have a heavy rain, 10 millimeter? Cannot. But they can tell you 70% of the time there is a probability there is going to be heavy rain and might exceed certain millimeter. So this is also prediction. Okay? So you cannot predict exactly, but you can predict the range. So you cannot select the second one. And then for the last one, of course, is wrong. Because when you talk about random behavior, 67%. Okay? You cannot even classify 100%. Because usually you only cover 99.9%. That is plus minus 3 sigma. Okay? Plus minus 3 sigma doesn't even cover 100%. You only cover up to 99.9%. That is the random property. Okay. Hope you have fun if you see your name out there. I hope we have time for the second one, but let's do this. Continue. Okay, the next topic is actually about current source. We are going to spend quite some time on this. Now, current source is very important. Actually, we keep telling people current source. There are actually two things. One is called current source, one is called current sink. This is called current source. This is called current sink. You know the difference? One is sinking the current, yes. One is sourcing the current. So if you talk at the circuit, you can see circuit is here. Okay, this is sinking the current. For this guy, you are sourcing the current. Okay, so one is source, one is sink. But some people, or most of the time, we actually don't differentiate. Okay, we just call them current source in general. Now, current source, the typical structure is always like this. You will have one branch establish the reference current, and that always consists of diode-connected transistor. Diode-connected transistor. You use that to establish the reference VGS. And with this VGS, you apply it to other branch. Because other branch have the same VGS, they should have the same current. Okay? But it will be very inefficient. Think about that. If I use 1-to-1, meaning that if I want to establish 1 milliampere, I use 1 milliampere. Then about 50% of the power is actually wasted, if you think carefully. Because only 50% is used for the real function. The other is just used for establishing the reference. Not that useful. So usually people, you use current mirror ratio. So for example, a common choice is 1-to-10. So for the real circuit that you want, you use 10 times the current. For the circuit that you only try to establish the VGS, you only use 1 time. So that you only waste 10% of the power to just establish the reference, which is actually just perform a very simple voltage establishment function. Very simple. One thing that students make the mistake is that I have seen student design. So this guy, they design 10 micron by 1 micron. So this guy, they say, I want to have 1-to-10, right? So let's use 0.1 micron, 0.1 micron. Okay, anywhere, right hand side is 10 times, left hand side is 1 times. We are talking about W/L ratio, right? So that is 1-to-10. Now that is very bad choice. When we talk about current mirror, the reason current mirror work is because they are identical. Okay? So if you are talking about 10 micron by 1 micron, then the other guy, at the very least, you should use 1 micron by 1 micron ratio. But in fact, if you want really good result, you should actually do this. 1 micron by 1 micron. This guy also 1 micron by 1 micron, but you multiply by 10. That will give you the best result. You should treat it like a twin. If you want 10 times exactly the same twin, they should come out exactly identical. You get the point? You can create 10 finger. So usually, let's say you create this guy identical, so there is one side, right? Then the other side, what you do is you create something like this. 10 of them. Okay, and then this will actually create exactly identical one. You don't want to do something like this, and then you create something like this. They are not going to give you very good current mirror. You get my point? Okay, because they are not identical. Okay, even this one is not identical. I think we covered that. So what do you need to do? Usually you do something like this. Okay, 1 to 10 is too big. Let's do something like this. Let's do 1 to 4. Okay, so I'll pick this 4. I'll pick this guy. How about the other? Let them float. Okay, that is so-called dummy. So this would be the something like, I think, source, drain, source, drain, source, drain, something like that. Okay, so you use that, and these 4 will be together, and this one is the one. Then you try to make them match. So that is actually better. All the single transistor will see the same surrounding. They will have better match. Now, I want to mention this because I've seen that last academic year when students design the current source, they anyhow design, as long as they think that the ratio are the same, are okay. No, they need to be identical. So here, just a simple calculation. We want to make sure VGS is the same. Therefore, since the current is only depending on the sizing, so if the sizing ratio W over L exactly obey the current ratio, then you will end up having exactly the same current ratio. Okay? Now, in reality, there will be some mismatch. Why? Because on one side, your VDS is exactly same as VGS, but on the other side, your VDS can be anything. So the current is only identical provided the VDS are also the same. The reason of the mismatch is because it depends on where is your VDS. The current at this point and the current at this point is not exactly the same. But of course, if you can make very flat something like this, then it doesn't matter whether it's this point or whether it's this point, the current is quite close, identical. Okay? Another thing to note is that we all want M to be large. Because if M is large, the power reduced. Just now 1 to 10, right? You only wasted 10% power. If 1 to 100, you only waste 1% of the power. Okay? But usually, you know nothing is free. If you do that, when you have more current mirror ratio, the noise actually gets worsened. This is very typical choice in visual design. Okay? In visual design, we usually try to mirror the current to supply the visual, but the more you mirror, the worse the noise. So there is a trade-off, whether you want to burn more power or you want to get better noise. Okay, so you know this simple current source is not as good as ideal. We want to make it as ideal as possible. And what is ideal? Ideal means I want it to be flat. The flatter it is, the ideal it is. Okay, so how to achieve flat? We learned this last week. We know that looking into the drain terminal of the MOSFET, if I have some resistor at the source terminal, I can actually boost the resistance. How much I boost? I boost by this factor. So the larger the R, the larger the resistance looking into the drain terminal, and therefore the flatter it is. And that actually brings us to the concept of cascode. So why we don't use resistor here is because there are issues with resistor. The larger the resistor that you insert over here, you need to sacrifice IR drop. The larger the R, the larger the drop. Okay, so your current source will look something like this. You only behave like a current source beyond this region. Within this region, your transistor is operating in linear region, and therefore you actually have very wide linear region. So if your supply voltage is only up to here, which means you can only operate the current source in this narrow region. That is not good. So that is the reason, that is the disadvantage of having a resistor. So one way to solve it is we can use not real resistor. We use fictitious resistor, the one that presented by MOSFET. Okay, this guy actually presents a R0 resistance, but it doesn't require IR0 drop. It will give you R0 as long as the voltage is bigger than VDS set. As long as the voltage is bigger than VDS set, the transistor will go into saturation region. If the transistor go into saturation region, you will have a resistor R0. Okay? So, using this cascode transistor, it successfully gives you a way to boost the output resistance by this factor without sacrificing the voltage headroom. So the voltage headroom is better. It looks something like this. So it can behave like a current source, a high resistance current source beyond this region. Okay, much wider. But still, it's not optimal because if you look carefully, it only behaves like a current source. Ideally, you only require VDS set here and VDS set here. So 2 VDS set will be sufficient for you to have good current source, right? Cascade current source. But because the way we achieve this current source is we have VGS. We have another VGS, right? And then we have another VGS drop here, and then we add another VDS set. So actually the minimum at this point is actually given by VDS set plus VGS1. Okay? So the minimum we can go is actually 2 VDS set. But because of this biasing, the minimum we can go is this guy. It's larger. It's larger. So although this is better than register, but it's still not that good. So the goal doesn't change. We still want cascode. We still want high resistance. But the question changed. The question changed now is not how to obtain the higher resistance. We know how to do that. The question changed now is how to get higher resistance with minimum voltage headroom. Okay? And the minimum we can go 2 VDS set. If you have 3 transistor, 3 VDS set. Okay? So if you know this requirement, then to answer the question is quite easy. I know this guy only required VDS set. This guy only required VDS set. Okay? So this point is VDS set. Now, as long as I bias this point to be equals to VDS set plus VGS, my job is done, right? If I make VB equals to VDS set plus VGS, then M4 will be able to operate all the way down to 2 VDS set. Agree? This is simple KBL, nothing special. Okay? Just now that one doesn't work. Why? Because just now that one is actually 2 VGS. It's more than what you want. Actually, you only require 1 VGS plus 1 VDS set. That will do. You get the point? So if you know this requirement, so cascode design is all about way of obtaining VB. We already know what we want. We want 2 VDS set. And we also know the VB has to be VDS set plus VGS. So the remaining job is, how do I get VB to be VDS set plus VGS? Think carefully about this. I find that a lot of students confused about cascode because they find it very complicated. How come you need to design this? How come you need to design that? But eventually they all come down to a very simple principle. I want 2 VDS set. So I know that this voltage needs to be VDS set plus VGS. The rest is figuring out how to get that. That's it. Simple as that. Okay? So this branch usually is like that. We don't change. This branch is important because you want to establish what is the VGS needed to set up the current mirror. Okay, so this branch usually is always identical and is always connected in this manner. You don't touch. Okay, it's always like that. So the cascode design is all about figuring VB. A very simple way of figuring out VB, the first method, just establish another current mirror. Okay, just use M5. And then your job is basically just to make sure your VGS phi is exactly equals to VD set M2 plus VGS M4. Right? That is exactly what we want. So as long as you are able to achieve this, your job is done. So how do you get VGS phi? So based on the current pumping, you can actually, based on the square law, you obtain the following. Okay, expansion, we want it to be equals to VGS M4. So, but don't forget, VGS M4 and VGS M3, they are identical. So this is actually VGS M3, but it's also VGS M4. And then what is the VDS M2? VDS M2 is actually equals to VDS set M1. So they are actually identical. I told you already, this branch and this branch, they are identical, right? So from the equation, if you understand the logic, it's not that difficult to formulate. Okay? This gives you the VGS and phi, you need to make sure they are equal. And then the rest, you just do the mathematics and figure out the sizing. Now, of course, here I lump the VTH phi and VTH3 together and call it delta VTH. And after, because M3 and M1, they're actually identical, I can actually sum them together and becomes 2 times. So in the end, I end up having this very simplified formula. If I ignore the delta VTH, I can actually right away derive this sizing. So very straightforward. But the problem with this method is that 2 things. One thing is, there is this delta VTH. Why? Because VTH3, this thing, the body and the source terminal, they are not together. So therefore, the VTH is actually suffering from body effect. But this VTH phi, you can see that these two are shorted together. So the VTH phi actually don't have body effect. So these two VTH, they don't match. That's why they give rise to this delta VTH. So there is one problem. Now another problem you probably see from this equation. You are trying to create VGS phi to track VDS and also VGS M4. Now in IC design, one trick people use, right? If you want everything to work out nicely, usually you want to, this guy follow this guy follow this guy. One guy track one guy. Okay? So this transistor track this transistor, another transistor track another transistor. So when this guy is changing, it follow this guy. When this guy is changing, it follow this guy. That is usually the principle people are doing. The problem with this technique is that you use one transistor and you try to track 2 transistors. You get the point? Too busy. Okay, the transistor is too busy. They cannot follow. So this technique works, but doesn't work that well because of these 2 problems. The threshold voltage problem, and you are trying to use one transistor to track 2. So that brings us to the second technique. Okay, the second technique. So here you can see we insert one more transistor, M6. So still same thing. This is actually VB. You already know what you want. You want it to be VDS set M2 plus VGS M4. You know what you want, right? So how to form VB? Now if you look carefully, VB is basically given as VGS phi plus VDS 6. Okay, VGS phi plus VDS 6. Straightforward, right? Now, you make M5, M3, M1 to be the same. That gives you a very good benefit. Now your M5 will track M3. Which means when you try to form these two, your VB, one of the component given rise by VGS phi, already automatically track one of the component. So why tracking is so important? Because you think about when you design a circuit, let's say temperature change. So this transistor temperature increase. This transistor temperature also increase. But because they are identical, so they should change the same way. You get the point? So if this is VGS M4. So if VGS M4 change accordingly, because your VGS5 track this guy, you also change the same way. So you don't have to worry. That's the reason why we want them to track each other. So now you only need this transistor M6 to properly track this guy. Then your job is done. Okay? So we go through the derivation. Your VB is given by VGS6, but it also means equals to VDS6 plus VGS5. Okay? And then your VDS6, okay, we actually design the transistor M6 to be in linear region, so you can actually write down the linear region equation for the transistor M6 accordingly. And then you know that your VGS6 is actually given by VGS5 plus VGS5 plus VDS6. But this VDS6 subtract away this guy, so you end up having 2 VDS6. Okay, over here. And the threshold voltage is the same. And then now, there is the beauty. You use VGS5 to track VGS3. And then now you use VDS6 to track VDS1. Actually, alpha, you can select it to be 1. The reason you usually give an alpha margin, that is design margin. If you make it to be exactly identical, if it doesn't track very well, then the transistor might not be in saturation region. So usually you try to give it slightly larger. Okay, so even, let's say they don't track very well, all the transistor will still be in saturation region. That is the reason why you introduce alpha, and usually it's slightly bigger than 1. Usually it's slightly bigger than 1. And then same thing, you can reformulate VGS5 as follow, and you can reformulate VDS1 as follow. Okay, now you can, based on this equation, I think you substitute in, you end up having this guy. Very complicated, you don't have to remember how to derive. Eventually the important thing is about the derivation result, the derived result, something around this guy. Okay? So eventually, if I make alpha equals to 1, and I assume there is no threshold voltage difference, okay, so you end up having this simple derived result. The problem with this design, now there is only 1. Okay, unlike the first method, there is 2 issues. This design, only 1 issue, the threshold voltage doesn't match. The threshold voltage for 5, there is a body effect. Threshold voltage for 6, there is no body effect. So therefore, there is a delta VTH difference over there. So it still suffers from one problem. So the body effect doesn't match. Okay, so this guy. But it solved the other problem. Now you don't have one transistor tracking 2. Now you have 2 transistors, each tracking the others. Okay? Now, good, we solved the issue using the cascode method 2. Cascode method 1 is very simple. How about this one? All this calculation is very giddy, am I right? You get overwhelmed by all this calculation, all the square root, all the W over L, all the alpha. You tends to get lost, am I right? Yes or no? You need to actually revisit this a few more times, work out the homework, simulate a few times, you probably will get better at it. Okay, but it's actually quite overwhelming. So that's why I introduced high swing cascode 3. You don't need a lot of calculation. In fact, it's actually quite straightforward. You just have to remember one trick. This trick. Choose very large transistor. When you choose very large transistor, you are going to get VGS equals to VTH. Now that is quite simple to understand, right? ID equals to half mu n COX W over L VGS minus VTH. Now ID is finite number. If you make this guy very, very large, then this difference is going to be very, very small. Am I right? Yes or no? Okay. So the trick is, if you pick a transistor size large enough, then the VGS is very close to VTH. Then how does it help us? So let's look at this technique. It actually doesn't need a lot of calculation. So as mentioned, this is still the same. This is still the same. Okay? The VB, what we want is VDS set plus VGS. Okay? Now, where is the VDS set? You look at this guy. If this sizing is so big, then the voltage here, the VGS phi, is approximately equals to VTH. Am I right? Yes or no? Too many drawing, you are probably confusing. If M phi is very big, VGS phi is approximately equals to VTH. Agree? Okay. Then what is this point? This point is actually VGS 6 minus away VGS phi. But it's approximately equals to VGS 6 minus away VTH. Agree? What is VGS minus VTH? VDS set. Isn't it? So if this is VDS set, then this guy gives you VGS, right? Which is exactly what you want, right? What we want. VB equals to VDS set plus VGS, right? So any calculation needed? No need. Okay, you just need to make sure how to generate VDS set. You pick one transistor very big, so it becomes VTH. So VGS minus VTH, that is VDS set. And then from there you add another VGS, that is exactly what you want. Very straightforward. So the key, choose large transistor sizing, and then you choose M6 equals to 2 times M1. Right? Why? Because if you look at the current source, this guy is IREF. But because here you are adding VGS to this point, actually M6 now have 2 current flowing through, 2 times the current. So that is the reason why you make the M6 to be 2 times larger than M1. That is the reason. Okay, and M7 equals to M3. So this guy will track M3. So the VGS will be exactly identical. Okay, so now VB, you see, equals to VGS minus VGS phi, but that actually equals to VTH. So this whole thing forms and becomes VDS set. And this guy is actually VGS, and therefore is equals to this guy. Very little calculation. Everything is intuitive. Of course, it's not accurate. Everything is approximate. But it gives a very quick way of quickly establish the biasing. So this technique, very simple, without too much calculation, just intuitive understanding. And this technique becomes very useful if you have multiple cascode. Just now, cascode method 1, cascode method 2, just simple 2 cascode, the equation is already overwhelming, right? If you have 3 cascode, it's even worse. But for this guy, to get more cascode, very straightforward, no need calculation. You can see, the first transistor, we just use it to establish VGS, so that is very straightforward. Now the second transistor, this one, we use it to establish VDS set. And then we add another one to form the VGS, so that becomes your second transistor. And similarly, if this is VDS set, this will be 2 VDS set. And then you add another VGS to establish the biasing for the third transistor. And for this guy also the same. This is VDS set, 2 VDS set. Then this guy is another VDS set. And then you also add another VGS. So the principle is always the same. All the transistor add VDS. And then if you want the other biasing, you just add another VGS. That is the principle. And the sizing is also the same. You can see this guy track this guy. Now this guy still track this guy. But how about this guy? This guy is supposed to track this guy. But you have to be careful because the current amount is different. Here got IREF, but this current actually include 1/4 IREF, 1/4 IREF, 1/4 IREF. So it's actually 3/4 IREF. So therefore the sizing has to be sized accordingly. Now, how about this transistor? This transistor, now you see, they are 1/4, so it's actually half. Okay? Finally, this guy, only 1/4. So the ratio between this guy, it becomes 1/4. So the sizing is really straightforward. It's just that the current have to add accordingly. So the method 3, very straightforward. You don't need a lot of calculation. Now method 4 is actually the most complicated one. The most complicated one. Okay. All the method 1, method 2, and method 3 suffer from one key problem. Threshold voltage mismatch. Some transistor got threshold voltage that is body bias. Some transistor doesn't suffer from body bias, so the threshold voltage doesn't suffer from threshold voltage. The threshold voltage doesn't suffer from body bias. So the last method illustrates how we can actually totally remove the body effect difference. So these two is still the same, huh? This VB requirement is still the same. I want VGS plus VDS set. Remember that. So M5, straightforward. You want it to track this transistor, M4. So it should be the same sizing. Now this transistor, M6, should provide you the VDS set. Okay? Should provide you the VDS set. So the VB is given by VGS5 plus VDS6. Okay? So M5 need to track M3 and M1. Now here we set M7 equals to a ratio to M6 with a ratio of n, a factor of n, not ratio, factor of n. M6 is biased in linear region, so you can actually write down the linear region equation for M6. VGS6 and VGS7 are identical because they are shorted together. Now VDS6, you set it to be around some alpha factor of VDS1. We already mentioned why, because we don't want to be exactly 1. We need to provide some margin. Now VGS6 minus VTS6 is actually equals to VGS7 minus VTS7. Okay, straightforward because they share the same VGS. And therefore equals to VDS set 7. Don't be fooled, this is 7, this is 1. They are actually different. So then we can plug all these equations into here. Okay, so we get this guy. Now this is saturation current equals to IREF. This is linear region current also equals to IREF. So this linear region current for M6 has to be equals to the saturation current for M7. Okay, and after manipulating, you turns out having a quadratic equation over here, and then you will end up having this following formula over here. And you notice that among solving all these things, the threshold voltage never appeared. So therefore, this whole method doesn't suffer from the threshold voltage mismatch. So by assuming alpha equals to 1.1, n equals to 0.5, you go through the quadratic equation. Eventually, you end up having this formula. So this formula have a few advantages. This method has a few advantages. One thing, it uses two transistors to track two things. One transistor tracking VGS, another transistor tracking VDS. So that is what we want. Good. Second thing, because of the additional branch, it totally removes the threshold voltage difference. So that is another good thing. Okay? So what are the bad things? By now you should know. No method is always win. There is always problem. So one of the very straightforward method is that you see all the other method only required two current source. This method required one additional one. So it burns more power. So nothing is free. We use additional one current branch to get rid of the threshold voltage effect. Okay? So you need one more compared to two in the previous method. Now it could result in large device ratio. You can see that M1 and M7 is almost 10 times different. Okay? It's almost 10 times different. And that is assuming, I think, Sorry. Did I calculate correctly? Yeah, okay. The ratio is about 10 times different. So we could end up having a very large device ratio. So this is one of the drawback of this method. But if you really want to perfect matching current source without high swing current source without any mismatch issue, so you have to go with the method 4. More complicated. Now for BJT, we don't have so many methods, so we just covered a few. This is the simplest one, current mirror. The BJT is not as good current source compared to MOSFET. There are a few reasons. So one thing is finite current gain. Okay, so this finite current gain, you know that unlike MOSFET, it doesn't draw any gate current, but here actually they draw the base current. So this current and this current, inherently, there is already mismatch. You can see I0 and IREF, they are different by this additional factor. So that is the problem with BJT. Another problem is also the VCE, any difference in VCE will cause the difference in the current between the two branches. Okay? BJT also, one of the issues you probably learned, no matter how much you cascade, the maximum resistance that you can get is always beta plus 1 R0. Okay? So this is the maximum you can get. You cannot get more than that. One way, straight away way to improve is very similar to the so-called Darlington pair. So you include one more transistor over here. The good thing is that by doing that, you are actually making sure the current is actually smaller, because unlike here, okay, the IREF right away branch out to the beta. But here, although there is a IB, because of this additional transistor, now it becomes IB divided by beta. So the amount of current that is actually being drawn to supply to the Q1 and Q2 is actually smaller. So therefore you can see I0 and IREF now is actually closer because of this additional beta introduced. So more closely matched. Now without current source is commonly used if you want to get very, very small current. It actually doesn't give you the exact solution. You have to do iteration or simulation to get it. So the key idea is very simple. One side you have the VBE. Okay, VBE usually is very small, about 0.7. So you apply this 0.7 volt, spread it across another VBE and the resistor. Because of that, you are going to make this VBE very small. Very small. And you know the current depends on the VBE. By suppressing or by compressing the VBE on the other branch, you are able to compress the current going through the other branch. Okay? So you can see that VBE1 equals to VBE2 plus I0 R. So you try to make VBE2 very, very small. So therefore the current result for Q2 will becomes very, very small. And if you solve this thing, you don't get the exact solution. You get something like this. So how do you solve this? You plug in one I0, solve it, and then you update the I0 again. So through iteration, you can solve it. Okay? The technique is good if you want to obtain very small current. How small? Maybe nanoampere or sub-microampere. Okay? This technique will be applicable. Wilson current source. So here, just now what we show is the cascade current source. You can see that the transistor is connected in this manner. Now Wilson current source is different. You see that this guy is connected as a diode connected transistor. But you will be mistaken thinking that the RR is actually given by this guy. So the bottom resistance you see is only 1/GM. So therefore the output resistance only boosted by this factor. And this factor is not a lot, to be frank. This factor is not a lot. So you might be mistaken thinking that is the case, but that is not. The reason why it is different is because there is actually a feedback mechanism. So when the current going through this guy, whatever the voltage established, you actually feedback through this transistor and adjust this value. So there is actually a feedback mechanism. If you look at the cascade thing, there is no feedback mechanism because once the current going through here, you know that whatever the voltage here doesn't get feedback and appear here. They don't. Okay, so there is no feedback mechanism here. So how to analyze this guy? So we go from fundamental. We replace this transistor with hybrid pi, which is this guy. We replace this transistor with a diode connector transistor, which is 1/GM. And then we replace this transistor with another hybrid pi. Okay? You just have to remember the output of this guy is connected to the input of this guy. So therefore, this current source is somehow related to V2. It's somehow related to V2. Okay, so now we can start deriving. So based on this structure, your V1 is simply given by Ix multiplied by 1/GM2. So this is the Ix. This is 1/GM2. Now your V2, once you establish V1, you get the current source multiplied by R01. That is how you establish V2. Okay? And then your Vx. Your Vx is given by your V1, which is this guy, plus whatever the current flowing through R04. This is the current flowing through R04, which is basically Ix. Subtract away this current. Okay? And then you multiply by R04. Okay? And then you rearrange the equation. Very complicated. I'm not going to bore you with the detail. After some derivation, okay, and some simplification, you find that actually the output resistance is also boosted by this factor. So it's boosted by GM R0 factor. So if you look at one transistor, it's R0. So with this Wilson current source, it's actually boosted by GM R0. So therefore, the R0 becomes GN R0 squared. Okay? Now that is actually quite a tedious way of deriving. How can we simplify the analysis? We can make use of the feedback. Okay, in feedback, you know that if there is a series feedback, it tends to boost the resistance by the loop gain. Okay, so we know there is a feedback mechanism here. So let's try to determine the loop gain. So the loop gain, to obtain the loop gain, we first break the loop. We starting from this point, try to go through the whole loop and figure out the loop gain. So after breaking the loop, we get this guy. To figure out the loop gain is basically starting from Vi. We go through a circle and reach V out. So the loop gain is quite straightforward. You can see over here. Starting from Vi, what we have is actually a common drain amplifier. A common drain amplifier is given by this guy. Okay? Common drain means GMR, if you recall, 1 plus GMR. Okay? That is common drain. Due to body effect, this guy will change to GM minus GMB. So that's why here. Okay? And the R is actually diode connector transistor, so therefore over here. Now that actually tells you the voltage at this point. And then after you reach this point, you will encounter GM1, a common source amplifier, multiplied by the total resistance at this point, which is R01. So after going through the loop, this becomes the whole loop gain. If we assume GM4 about the same, this guy about the same, okay, so what we get is approximately GM R0. So the loop gain is about GM R0. Now, we already tells you the feedback. This is actually series feedback. Why do I say series feedback? You're actually looking into here. Whatever you get is actually added to the output. Okay? So because of that, we actually boost the gain, boost the output resistance by this loop gain. So if the output resistance, when you look at it, is R0, by boosting this loop gain, which is this guy, you also end up having GM R0 squared. So this is a simple way of looking at it. Now, usually you will try to make it balanced. The reason is you don't want to make this transistor VDS to be very different from this transistor VDS or this transistor VDS. So by adding additional transistor, you sort of balance out. One side C2 VDS, the other side also see 2 VDS. So they sort of balance out. But it's still the same Wilson current. Okay, 7 more slides and then we can call it a day. Bear with me. Now, we learned about current mirror, and one of the things that you learn from current mirror is that you make the resistance large. Now, this resistance is different from the passive resistance here. Here you can see that if I use the passive resistance, if I want to make the resistance large, the drawback is I'm going to suffer IR drop, very big IR drop. Agree? Right? And this IR drop, in the old days, you have 5 volt supply, no issue. Nowadays, with 1 volt supply, we are going to run out of headroom. Right? So, one possible way is actually replace this resistor with active load, such as transistor. We know a beauty of transistor is that it can give you very high resistance, R0, but it doesn't require very high voltage headroom, because as long as it's bigger than VDS set, it will give you R0. So that is the beauty of active load. Now, the problem with active load is that what is the DC voltage at these 2 points? You don't know. Why? If you assume an ideal current source like this load is infinite. So eventually, where is the output voltage? It could be this point. It could be this point. It doesn't matter. Am I right? Right? It could be this point also. So the problem with active load is that you don't know what is the final DC voltage you are going to get. Okay? So if you want to use the active load, especially the differential one, you always require common mode feedback. So you feedback the common mode. You measure the common mode voltage. If it doesn't locate at the value that you want, use the feedback mechanism to adjust it. So that is the drawback for active load. But this is the price that people are willing to pay. Now here, instead of using the common mode feedback, this is another way without the need of common mode feedback, because it doesn't have differential output. You only have single ended output. So here, this is the typical structure for op-amp, the first stage op-amp. You have the differential pair, we already go through it. At the top, instead of having resistor, we just flip the current mirror using PMOS current mirror. Connect on top. Now, how to analyze this circuit? So, the top one, this is differential, and this is the common mode. So, for the differential wise, let's look at the current. So, when your one side have VI over 2, the other side have minus VI over 2, let's figure out the current output. The current output is simply given by I01 minus I02. That will be the output current. Okay? And again, we make use of the seesaw mechanism. So this is actually a virtual ground. Okay? Although the circuit doesn't look symmetric, but because the differential pair is exactly the same, so you can still assume the seesaw mechanism. So when one side is going up, current go this way. When the other side going up, current go the other way. But this point never move. So therefore, this is still applicable. So with VI over 2, you will generate current given as GM VI over 2. This current will go through this transistor, which is 1 over GM. So I've shown it over here. And once it establishes the voltage over here, this M4 will create another current multiplied by GM4. And GM3, GM4, they are the same, cancel out. So you end up having I01 is simply GM1 V1 over 2. I02, your applied voltage is actually negative VI over 2. And you multiply by the GM of the M2, which is the same as GM of the M1, so I just use GM1. Now I0 is the subtraction of these two. You use this guy, subtract this guy, you end up having GM VI. So this OM structure eventually give out the output current exactly the same as common source amplifier, GMVI. And once you know the output current, to figure out the gain, you just have to multiply by the total output resistance at this point. The total output resistance at this point is R04 parallel with R02. So you got this current, you multiply by the output resistance, that is how you get the voltage gain. So the analysis is quite straightforward. In common mode analysis, we can also split. We split this guy as half current source, and the resistance becomes 2 times. So we can also go through the same analysis. The I01, again, this is actually a common source with degeneration. So the current is actually given by this guy. And then you multiply by 1 over GM3. And then you multiply by this current source cell, this common source amplifier, GM4. This guy cancel. Okay, so you end up having this structure. For M2, also the same. You also have this common source with degeneration amplifier. So you can write down this guy right away. Now the output current difference, you just take this guy, subtract away this guy. If there is no mismatch, then everything cancels out. You get 0. Okay, 0. And the common mode rejection ratio will be infinite. Now if there is a mismatch, what are you going to do? You do the same. You assume this guy to be GM plus delta GM over 2. So this guy will be GM minus delta GM over 2. Okay? But for this guy, you also have to do the same. This guy will probably do GM prime plus delta GM prime over 2. This guy will do GM prime minus delta GM prime over 2. You have to use GM prime because GM3, GM4 are different from GM1, GM2. And then you go through the analysis. You will be able to derive the common mode rejection ratio with mismatch. So this is exactly what we are doing. You can see over here. Okay, the GM1, GM2 is GMN, NMOS. So I use the following. The GM3, GM4 is GMP, PMOS. So I use the following. After some manipulation, you end up having the following. The common mode gain becomes this guy, and this is the common mode rejection ratio. Okay, you can see how it depends on the mismatch of the NMOS and the PMOS. Okay? Okay, let's go through this example, and then we are done. So this OM design, although look a bit different, but this guy we just covered. So this is the active load, OM, and this guy is just second stage common source amplifier. So this is a 2-stage design. The first stage is what we just designed, the differential. We just analyze the differential amplifier with active load. The second stage is common source amplifier, also with active load, a current mirror. So the gain is 60 dB, the total current is 2 milliampere. So here, how do we perform the design? In 2-stage amplifier, it's not clear to you. Now just take my word for it. So in this design, it's desirable to make this GM much larger than this GM. We want to make this GM much larger than this GM. So we want GM6 much bigger than GM2. Not obvious to you because we haven't covered the compensation. Okay, the compensation for stability concern. Here, just take my word for it. We need to make this guy in order for the OM to work better. Now, with 2 milliampere, we have to decide how to split the current. So a natural split is, this is 2-stage. Both stages are important. So let's split one stage 1 milli, the other stage 1 milli. So that is what we are doing. Okay? So we are doing this stage 1 milli, this stage also 1 milli. Okay? And we also split the gain equally. 60 dB means linearly the gain is 1000. So if you want 1000, take square root because you have two gain multiplied together. So each stage will give you 32. So the differential ones will give you 32. The common source stage also give you 32. And based on the current and also the parameter, we can already work out all these output resistance accordingly because 1 over lambda ID, right? And lambda already tells you, okay? For M7, we use the longer channel. Actually, for all the current source, we can use longer channel. Longer channel will make the lambda even smaller, so you can get higher output resistance. Now, why current source we can use longer channel? Because we are not driving it. Unlike this guy, you have signal driving the gate. So you want the parasitic to be as small as possible. But look at this guy. This guy is fixed. DC voltage. So you can use large transistor, doesn't matter. You only see this guy, drain here. But the drain doesn't see the gate, right? So actually using large one doesn't matter. Same thing for M5. So you use longer channel to make the resistance larger. So with all this, the differential gain we just analyzed, right? The differential gain from the differential input to this output is given by GM R04 parallel with R02. So we can figure out the differential gain over here, 32. R02, R04 we already know. So your GM1 need to be about 4.5 milli. Since I know the ID1 is 1 milliampere, I can work out my W over L for M1. The common source amplifier, GM6 multiplied by R06 parallel R07, also quite obvious. So this is GM6. The resistor here is R06. The resistor down is R07 parallel. Okay, so that is straightforward. We also want the gain to be 32. R06, R07, we already get it. So GM6 is about 7.1 milli. So it turns out, fine, GM6 is still bigger than GM2. Okay? Anyway, GM1 equals to GM2. So that tally with what we want. Okay? And given the ID6, 1 milliampere, we can actually figure out what should be the total sizing for W6. The M6, sorry. Here I make a mistake. ID1 is not 1 milli, it's actually 0.5 milli. The reason is you have 1 milli here. So this will split half, 0.5 here and 0.5 here. So M1 only see 0.5. So if you find that GM6 is not much bigger than GM1, one way you can do, redistribute the current. For example, making the first stage to be 500 0.5 milli, and then the other guy having 1.5 milli. That will make GM6 even larger because GM6 you are going to have larger ID, okay? And then the GM1 will have smaller ID. Of course, your gain probably cannot be equal. So you probably want to allocate more gain for the second stage, less gain for the first stage, accordingly. So, like I say, what I've shown here is not the final design. There are a lot of things for you to play around. When balanced, VA equals to VGS3, so M6 is mirror from M3. What do I mean? So if you consider everything symmetric, this guy match this guy match this guy. So if you think carefully, if everything is balanced, the current here and the current here are identical, there is no reason why this voltage is not the same as this voltage, am I right? Right? Everything equal. Although it looks asymmetric, but if you think carefully, same current going through both branch, exactly identical M3, M4, so they should behave similarly. So therefore, VA should be the same as the VGS for M3. If that is the case, then the M6 can be considered as mirror from M3. Right? M3 is diode connected transistor. So because of that, therefore you can actually deduce the current. ID6 is actually 2 times ID3. And therefore, your M6, M3, M4, M6 should be double of M3, M4. Therefore, M3, M4 is half of M6. And that is how you derive the sizing. Now, the rest is basically trying to work out whether the transistor is operating in saturation region or linear region, right? So, from all this sizing, you can work out VDS set 4 and VDS set 6. The VGS tree can also be worked out accordingly. Okay? Choose VDS set 5 and VDS 7 to be 0.3. What do I mean? M5 and M6 is actually current mirror. Okay? So for current mirror, as long as the VDS is bigger than this VDS set, the transistor is operating in saturation region, everything is fine. So here, I'm choosing this guy to be 0.3. This is actually, I believe, operate in 3 volts, so therefore I have sufficient headroom. So I allocate 0.3 for this transistor. VDS set to be 0.3. VDS to be 0.3. Now, if you don't have sufficient headroom, you can lower this guy down to probably 0.1 accordingly. So here, allocating it to be 0.3, and I know what the current that is needed, I can actually work out the sizing. And you can see that I don't use the minimum sizing. The minimum sizing is 0.35, so I use 0.7 here to make the resistance slightly larger. And then I didn't make the IREF to be exactly the same. I make it 10 times smaller. So therefore, I can also figure out the transistor sizing for the M5 and M8. Okay? Now for the amplifier, it's very important to determine the operating voltage. What do I mean by operating voltage? Suppose this is the voltage. What is the minimum it can go? What is the maximum that it can go? Suppose this is the output voltage. What is the minimum it can go? And what is the maximum it can go? So to understand that, again, everything is based on saturation region. So the minimum it can go is basically VDS set M5 plus VGS M2. That is the minimum. VIC minimum. Okay? How about maximum? VIC maximum. You might be thinking it should be VDD minus VDS set M4 minus away VDS set M2 and then add back VGS M2. But you're wrong, because this is not the worst case. The worst case is this guy. So what you should have is actually VDD minus away VGS 3 minus away VDS set 1, and then you plus VGS 1. Okay, so that is the maximum that you can go. I believe somewhere here. Okay? For output, that is quite straightforward. For output maximum and minimum is basically just VDS set 7. The maximum is VDD minus away VDS set 6. Okay? So all these will allow you to know the design op-amp should operate within what voltage range. So in op-amp design, this is actually quite important analysis. Now, of course, after designing it, we need to run the simulation. So we go through the simulation, we target for 60 dB. We actually kind of short. We only get about 53 dB, so you need to fine-tune a little bit. Maybe make the GM larger, maybe redistribute the current. Redistribute the current got one advantage. By making some current smaller, we actually make the resistance larger. So the gain can actually be boosted. Okay? So I redesign some of the thing. Eventually, I can actually reach more than 60 dB. Okay? This is the final result. So, sorry for a bit rush for today's lecture, but I hope you get some idea. So today's lecture we covered RF amplifier design. So you roughly know what are the things to consider for RF design. And then we talk about cascode. Remember, it might look overwhelming. All the algebra equation is so complicated. How can I remember? You don't need to. Have been derived, you just use it. exam is open book. Okay? Now, if you are so confused, look at the Cascode method 3. Cascode method 3, no need calculation. Just intuitive understanding. VDS plus VGS, VDS plus VGS, that's it. Okay? How do you get VDS? Make one transistor very big. So the VDS becomes VGS minus VTH. Therefore VDS. So Cascode method 3 is very simple. Method 1 is also very simple. Except that, not very good. Okay, it suffers from two problems. So you need to understand that. And then if you want more sophisticated one, you look at method 2 and method 4. And then finally, for the OM design, I know a little bit rush. We are going to go through more detailed design later. But the important takeaway is this. We don't want to use register because of the headroom. So in the OM design, we introduce the concept of the so-called active load. Active load, you get high resistance with very little voltage headroom. That is the beauty. And then the second takeaway is, in design there is no right and wrong. The first thing you do power budgeting. Okay, you decided how to split the current. As long as you can make your justification, that's fine. Okay? And be assured, you can never get the result right away. Okay, but that will bring you to close enough result. And then you fine-tune using the simulation. Okay? So that is the key takeaway. I just re-emphasize. Let me do this thing again. Can you scan? Should be quite fast. Another 2-3 minutes maybe. Done? Okay, activities. Lecture 3, 3B, and play. So it'll be quite straightforward, right? I hope all students get it right. All done? Okay, let's move on. Okay, still some students get it wrong. I think those students who get it right probably remember what I tells you. Can the resistance increase forever for cascode? Eventually it's going to be limited by the leakage. So the first question, the first answer is definitely wrong. Okay, it's not always increases with number of cascode. Okay, let's look at second one. This one very fast. Okay, 25 students already. I believe it's 25, so 26. Okay, all done? Okay, let's go. Okay, good. Most of you get it right. Okay, the beauty of active load is basically high resistance without occupying significant voltage headroom. The first one, is it an advantage or disadvantage? Disadvantage. It's actually non-linear resistance. Okay, so actually if you use it right away for open loop amplifier, you are going to suffer a lot in terms of linearity. Okay, so that is actually not good. That is not good. So it's not an advantage. Now the third one actually is the other way. The transistor occupy much smaller area. To get 100K, you lay out the real register a lot of area. You lay out transistor, occupy very small. Now, matching wise is a different story. Matching wise, we always like larger area. So for MOSFET and for register, always, you can make higher, larger area, matching is better. But you cannot talk about matching between register and the MOSFET. You can only talk about, if I use MOSFET to get the matching, is it better than using register to get the matching? Eventually, ultimately, it depends on the size. Okay? So that's it for today's lecture. Sorry. Okay, we'll call it a day. Sorry, today's lecture is a bit long.
Recording stopped.